So, welcome back, everybody. So, we're going to go through some physical properties of soil and look at some of those characteristics. Now, I know yesterday, I'm going to warn you, everybody was pretty quiet. So, I'm hoping there will be some questions. We'll get some volunteers to ask something. Don't be afraid to ask questions. Um, that's what we're here for to help you understand things. Otherwise, if I don't hear questions, I may have to start randomly calling on some people and we'll call you out and put you on the spot. But hopefully we'll get some questions. I'm sort of joking around with everybody, but honestly, if you have questions, if you're thinking it, I'm sure somebody else is too. So the first thing today we're going to go through is physical properties of soil, and then after a short break, again like yesterday, then we're going to talk about performing site evaluations. So with that, what are some physical properties of soil? One of the easiest ones that's most apparent is the color of the soil. You can take a look at it and you can see whether it's dark or light or otherwise, red or brown. You can spot that and be able to identify that. So, color system here, the way it works is that this was all done by a person named Munsell, and he came up with a way to identify colors. And this is for every color in the spectrum. So not just for soils, this can be anything out there. And so there's three main components. So there's the hue, and that's the dominant spectral color. So whether it's towards you see the spokes on the wheel there, whether it's a yellowish or a bluish or a reddish or a combination of them, like the yellow and blue make greens. So that's a dominant spectral color. And so there'll be a number for that, like 10YR. You've probably seen that reported. So that means 10, and between the yellow and red, and if you mix yellow and red together, you get brown. And then there's a value. A value is the relative light or darkness of a soil or of any color. So white on one end and pure black on the other end. And then there's chroma. Chroma is the purity or strength of a color. So, on your TV, you've probably seen like a color adjustment where you can turn it down where there's less color and it almost gets to black and white, and you turn it up more and more colors introduced until it's almost like clown-like. It's so saturated that it's, highly saturated color. And that's the same thing, is that you will have the chroma of the color is the amount or how intense the color is that there's very little color to it to more and more color introduced. And then we'll see that on the Munsell color book here. And we're going to skip out here. We're going to try something a little bit different. So here we've got, um, this is a Munsell color book. This is Jeff. Jeff's here with me. But Munsell color book. So we'll just sort of go through and sort of show what these look like. So we have these color charts in here. And let me zoom in a little bit and like that. So you can see these color charts, um, protective slide here, but you can see that, here again, we have the color page. It's the 10R, and then we have um, our value, the light or darkness. So it's light on this end, dark on the other end, and then the chroma, the intensity color. So you can see, especially like on this row, basically it's gray, it's black and white. And as we add more and more color as it goes across, the color gets more and more intense. And then we'll have different pages as we flip through. You can see like here's the 10YR page for us. Again, the page here indicates what the color is, and then we have the values that go from light down to dark, and then we have the intensity color that goes from grayish to greater color intensity. So that's how that works. Our color charts as we go through, you can see just like these pages here, there's the one page that we pulled out. We have our 10YR color here for a color page, and then again, our value and our chroma. So each of the different pages that we have in there, we can go through all the colors that we have for soil. There are additional pages that aren't part of our book, but you could do a color, purple. There might be a purple or a green color or something if you want to. I'm sure there's other Munsell books for every other color under the sun. So the way we report this is hue, value, and then chroma. So when we write it that way, we do the hue, the 10YR, the value, 4, and a chroma 4, and we put a slash in there. So a 10YR 4 is the 10YR page. We're a value of 4, and we're a chroma of 4. It's sort of hidden under the circle here, but that would be this color chip right here. So that is the 10YR 4. Now, although colors are easy to identify, we do have a few things in the code relating to some soil color, but a particular color on its own doesn't necessarily mean that the soil is going to be good or bad. Just because we have 10YR44 doesn't mean it's good. Just because we have 10YR72 doesn't mean it's good or doesn't mean it's bad. It's the relationship that you see of the colors to each other in the different horizons. That's what's going to indicate whether something is good or something bad. We had some questions about how do we know is fill. When we see color patterns that aren't quote normal or not through normal soil forming processes, we see them as an issue. So where do some of these colors come from? Surface coatings impart color. So I mean the soil itself is naturally colored, based on whatever it is. So if you have quartzite or quartz that's sort of clear, cloudy in color, that's the color of the soil. It's naturally going to be very light colored. If you have something like I mentioned, the rotten granite that we had, and that's sort of a reddish and black, that's going to sort of impart some of your soil colors. So black organic matter is going to make a darker soil color. The reds, browns, and yellows are different iron oxides. And then the gray that we have can be a natural color on the soil, or it could be a lack of organic matter and iron oxide. If we don't have anything covering it up, it could be gray, or the iron has changed color and has been bleached out of the soil, so to speak. Also, want to mention that winter conditions do adversely affect soil colors. Light conditions, low angle of the sun, you're more in the red spectrum, and it's harder to see things. You may remember if you had, the premiums. I'm dating myself, but back when cereal still had little trinkets in it, you'd get these hidden messages, and you'd have like the little decoder lens you'd put over it. It was like a red piece of cellophane or blue, and there would be red and blue printing, and then if you're viewing it through that red lens, the red would disappear and you'd see the blue underneath. Same thing here. If you're trying to look for red splotches of color or red soil colors, and your light condition is red sunlight because it's low angle, or if you're in the summer real late towards the day when the sun's starting to set, you're not going to be able to see certain things because of the color spectrum of light. It's going to affect it. Many of you may have seen, like in a house, that you paint a wall, or you pick a color out at the Home Depot or Menards or whatever, and you come home and paint a wall, and it doesn't look like what you thought because their lights are different than the lights you have at home, makes the color look different. Also, frozen soil ice crystals reflect the light. It's going to be hard getting a good, accurate color if you're looking at those kind of frozen soils. So, what do some of the soil mineral colors impart? What are the colors that we're dealing with here? So iron compounds coat the surfaces of individual soil particles, and iron is common in the Earth's crust. It's everywhere, and that's what's predominantly coloring soil. So you can see sort of the chart here of these 9 colors. They're all brown of some sort, brownish yellow. So why is mostly soil brown and reddish? Because that's the iron in it, and that's what's giving us the color. So different iron compounds impart various soil colors as shown there. And when the iron colors are removed or the iron coatings are removed, the natural soil particles can be viewed. And a lot of times they're grayish or flecks of black or whatever, but they could be, like I said, whatever, depending on what that mineral is. But just be aware that on here, the various iron, and we'll talk more about this when we get into redoxamorphic features, but these different iron colors tend to lean towards different things. Is that the darker ones tend to be more oxidized, where the lighter color ones tend to be less oxidized and are more compounds that are related to wetness usually, but not always. And like I said, we'll talk more about that in redox and get really down that rabbit hole. But usually the darker red or brownish colors tend to be a more well oxidized kind of iron. So the low chroma colors, we mentioned that, and again, we'll get a lot more into how redox occur and what they are. But low chroma colors, and so having low chroma or towards the black and white end of the spectrum is a value of 4 or more and a chroma of 2 or less. So if we're in that zone right here, that can indicate that we have depletions. So if the iron's been removed off of the surface of the minerals, or it's a reducing condition, and again, we'll explain more about that when we talk about redox, but it's a change in the chemical composition of the iron due to it being submerged underwater for a period of time. So if we have low chroma colors in this zone, and it doesn't matter what page you're on, 10YR or 5Y or whatever, value of 4 or more, chroma or 2 or less, these are conditions that may indicate, should send a red flag up to say, we need to really look closer and see how these patterns, again, just because you have this doesn't mean that it's bad, but in relation to the other horizons and where it is located in the soil, it may indicate wetness. And then if we have suspicious conditions with chromas of 3 or less, so I guess yellow flag or a warning flag for these conditions, we may want to take a closer look at them. So when we're getting sort of the black and white kind of soils, we want to look carefully to see, are we having a reducing condition? Do we have some kind of redoxamorphic feature? Now, we talked yesterday about certain things like parent materials, and this is where it's key to know what your parent material is, because if we have a certain parent material and it's gray, then it's almost always a reduced or underwater kind of condition. Other parent materials, if they're naturally that color, it's going to indicate to us that that's just what it is. It's just, if it's clean washed sand and the sand's quartz and it's gray in color already, that's not necessarily meaning that it's reduced. It's just that's what the parent material is. And if we see any of these colors, now here you'll start to note we get some fun colors in here. So we have N7 dash nothing. And you're like, well, what's that? I thought we had to have a hue, a value, and a chroma. So what hue is N? Because I sort of understood when you said, YR for yellow red, or I can maybe guess what some of these are, like G for green or B for blue or blue green. But what's an N? N is neutral. So if we go back to where we had that, I can do it, that spindle here, it's neutral. There is no color whatsoever. There's basically no chroma. It's just a hue and a value. There's no chroma. So that's why when we report hue, value, chroma, since there's no chroma, it's an N, it's a neutral. There is no hue to it either. If you have that, if you have these that are the 5 Ys, the yellows, greens, blues, you don't see many soils that look like this, and if you do, this color chart is for clay. The clay color chart is basically soils that are underwater. If you see colors on this chart, most likely you're dealing with something that's very, very wet for a long period of time. So if you have to use this color chart in here, it's most likely a pretty bad site for you. So we sort of went through colors and identified some of those. So what are some other characteristics that we can identify in soil that's observable for us? The next one is texture. So the important thing to understand with texture is these things called soil separates. So soil separates or particle sizes are made up of three different things: sand, silt, and clay. So the first one is that anything under 2 millimeters in size is considered a soil separate. Anything over 2 millimeters in size is considered a rock fragment. And we'll talk about those in a bit. So soil is only under 2 millimeters in size. With that being, I know it's sort of small print there, but sand is between 0.05 millimeters and 2 millimeters in size. Silt is between 0.002 millimeters and 0.05 millimeters in size. And clay is from 0.002 millimeters and under. So it's sort of hard to, what is 2 millimeters compared to 0.05 millimeters to what's 0.002 millimeters. So an analogy or way to think of that is that if I had a piece of material that was 15 foot in diameter, like the swimming pool, that would be a sand particle. And then a particle the size of a softball, 4.5 inches across, would be equivalent to silt. So you can see how much different a sand and a silt particle is. And then a clay particle would be the size of a BB. So a BB to a pool, if I had one sand, one silt, one clay, would be like a 15-foot diameter pool, a softball, and a BB. So you can see how the different particles have such a different relationship to each other in size. I know, like, again, the numbers for millimeters and a decimal point are sort of hard to conceptualize, but that's how we would relate between them if we scale them up, so to speak. So now that we know we have sand, silt, and clay, the soil textures are the relative percentages of sand, silt, and clay particles mixed together. Now, on this textural triangle, for those that haven't read it or want to be familiar with how to read it again, the way we look at it is the silt is down the right hand side, clay is up the left hand side, and sand goes across the bottom. So if we're looking at something here, so something 35% sand, you can see 10, 20, 30, 35, or sort of between the 30 and 40 here. We would run up here, and this goes along. You can see these lines are diagonal here, and we'd be along this line up this way. So if we're basically 33% or 35% sand, and we're about 30% clay, that's going up here, 30, 40, whatever. So we're about 30% across here, and then we're like about 35% silt. That comes down this way, so you can see 10, 20, 30, 40, 50. And so if with three of these drawn in, they will get a spot in the middle, and that's how we would determine it. So you can do, a lab analysis to get these numbers. And the samples, if you ordered the kits, we have lab analysis on those, and we know exactly what the lab says it is. And the thing is that what we can do is we can train ourselves with our hands to physically texture the soil and come up with a range and be fairly accurate at it and be able to come the least to put them. Hopefully, we should all be accurate enough to put them in the major 12 textural classes. So the particles of sand, silt, and clay make up the 12 textural classes. However, the trick is, or one of the tricky things is, clay is also a textural class, silt is also a textural class, and sand is a textural class. Now, as you might guess, clay is predominantly made up of what particles? It's, well, here the lowest one is about 40 to 100% clay. Silt is made up of more than 80% silt. Sand is made up of more than, well, about 85%, 88% sand. So even though it's a soil separate, a particle, it's also a textural class. So again, the percentage of sand, silt, and clay, the particles, will tell us what the one of the 12 textural classes that it is in. And then you can see here. So a mixture of them here, basically about equal 35 sand, 35 silt, 30% clay gives us clay loam for a texture. So if we're 70% silt and 20% sand and 10% clay, we would be in the silt loam category. And so that's how we come up with our textural classes. So the important thing is when we do this, make sure that you're using one of the names. Don't make up a class. Every once in a while, I'll see somebody will say it's a silty, sandy, clay loam, and I don't know what that is. It's not one of the 12 textural classes. So make sure that you're identifying it correctly on here, and then also texture modifiers. So if there is coarse fragments that are above the 2 millimeter in size, we'll need to identify those also if there's a certain percentage. We'll talk about that in a minute. But you may have to use a textural modifier. So something such as very gravelly sand or extremely cobbly sand. We could do that for the clay too. You could have gravelly clay potentially. And then also we'll talk about textural subclasses. If you're in the sands, so sandy loam, loamy sand, or sand in that corner, we may have to further identify what kind of sand we have, whether it's coarse sand or coarse sandy loam or fine sands, because that's going to make a difference for us on our loading rate tables that we'll tie into later. So how do we do hand texturing of soil? And again, we'll get to practice this next week with your soil samples, and I'll show you how to do that on the camera. But hand texturing of soil, it's a field demonstration by feel. And there are and I'll show you some like flow charts, some templates, and sort of how to proceed to get an idea of it if you haven't done it before. But really, it's a process that you have to learn and you have to practice. It's not something that I can just show you 2 + 2 is 4, and you go, okay, yeah, I know how to do that. 2 and 2 is 4. It's and this is where soils gets difficult. It's an interpretation kind of thing. It's like showing you a painting and saying, what do you think of the painting? Well, I think they had a good use of colors and it's very majestic or something. Well, that's sort of your feeling on it. Now, hopefully, when we do this again, we can get to one of the 12 textures, but again, it's a training kind of thing. You have to sort of get an idea how much soil I need to put in, how much force I need to use. And it's a feel thing, and you have to practice. And the only way to know for sure is to do it based on known samples and say, hey, this is what I feel, and I know that this is a silt loam with this percentage of sand, silt, and clay. And you sort of train yourself that what I feel and then what you know to match those up. So when you go out in the field, you can be accurate. But hopefully, again, we get 12 textual classes. We should be able to do that without a lab analysis, and then we'll be able to practice that next week, some texturing. But this is what the flow chart looks like. The keys to doing this is that the sample has to be moist. You don't want it soggy wet, but it has to be a moist sample. And especially if you have a heavier textured soil like clay or something like that, you're going to have to work the lumps out of it because if you feel the lump, it might throw you off that you think it's a piece of sand or something or a piece of gravel. So you're going to have to, get rid of those. And then it's sort of a feel, if it feels sandy, it's gritty. If it's sort of smooth, almost like a floury kind of thing, more like dough, that's going to be silt. And if it's in Wisconsin, if it's sticky, it's clay. And that's why if you do this and you learn Wisconsin, if you move far away to like say Georgia or something, you're going to have to retrain yourself because their clay is not going to feel like ours is. And then organic matter, that's also going to affect the feel. So if you have a topsoil, like in this picture here, with a lot of organic matter in it, it's going to feel different. The trick that I always used is 1% organic matter is going to feel like 4% clay. So it's just something you'll have to train yourself that if you feel two soils that feel exactly the same, but one's black and one's brown or grayish, the black one is probably going to have less clay in it than you think because the organic matter is acting like that or feeling like that. But again, practice makes perfect. It's something you got to keep up on. I know years ago we did soil judging in college, and and for the contest you had to get within 4% to get credit. And with practice, we were getting 1 to 2% off pretty consistently. And I can tell you right now, I'm happy I can get them in the 12 textures because, that was constant practice every week off of known samples. So we don't expect you to be that accurate, but we should be able to determine whether it's, clay or clay loam or sandy loam, silt loam. Should be able to get into 12 textural classes. So then we also talked about sand sizes. There are some, we use the USDA classification system for soil, and there's 12 textural classes, but there are also 5 sand classes. So we have very fine, fine, medium, coarse, and very coarse. And that breaks out, even though sand is between zero point zero 0.05 and 2 millimeters, the different sand is different categories. So very fine sand is between zero point zero 0.05 and 0.10. So just like we had mentioned on the diagram of the swimming pool, and the softball was at sort of the top end of silt. Well, what if I had a basketball in there? Well, that would still be sand, but that would be on the very fine end of sand compared to the 15-foot diameter swimming pool. Well, if I had a 10-foot kiddie pool, what would that be? Well, that might be the coarse one. So, I mean, there's some different ranges in there where, the 4.5 to 15 foot are different. So, same thing here is sand, especially, can really impart some characteristics on it, whether it's very fine or whether it's towards the coarse end. So, if you do have one of the sand textural classes, sand, loamy sand, or sandy loam, there are 4 subclasses in there. We don't really define medium, and we sort of lump coarse and very coarse together. But medium, we don't define. That is just if it's just sand, medium sand, we just call it sand. But if it's on the coarse end of the spectrum, we would modify it. And that first line here, COS, would be coarse sand, sand, fine sand, or very fine sand. And then we could also modify it for loamy, coarse sand, loamy fine sand, loamy very fine sand, coarse sandy loam, fine sandy loam, very fine sandy loam. So just be aware that if we do have these sand particles, we may have to break them out further in here, and they do get very technical about what coarse sand is. So first of all, it's the sand class. This is just a verbal representation of what that textural triangle showed us to get to 12 classes. And then this is the part we have to be aware of, is that a total of 25% or more very coarse and coarse sand and less than 50% of any other grade of sand would call it coarse sand. So if we're in the sand subclass and of the sand that we have, more than 25% coarse and very coarse and less than 50% of anything else, it's going to be called coarse sand. So here, this is the definition of loamy sand or sandy loam on the textural triangle. But again, the definition to make it coarse is a total of 25% more very coarse and coarse and less than 50% of any other grade of sand. So for subclass procedures, again, first we have to establish whether textural class. If we're in loam, we don't have to split out what kind of sand we have. It's irrelevant. But if we're in a sand, loamy sand, or sandy loam, we have to take that next step and break it down to say what kind of sand do we have. And you need to sort of estimate what the percentages are of those. So we're going to switch back to my camera here. There we go. We can see it. So if we're looking at our sand sizes, we showed you some pictures of what some of those look like. I've got some samples here. I know it's sort of in my jar, but this is what some of the sand looks like. This is fine sand. And what we've done is we've actually run this through a sieve and to determine what our sand sizes are. Jeff, you want to grab me one of the sieves out of there? It doesn't matter which one. But then what we do is we take this through our soil sample and we send it through a sieve, and you can sort of see our sand. And then here's some different ones. So sand for fine sand is the 140 sieve, and I think that's actually the one Jeff's holding there. So we run these through different sieves. Actually, this is a 250 opening here, but you'll have sieves. It's sort of not coming into focus, um, but anyway, we have these sieves like this, and you can see they've got a fine mesh screen in the bottom of them. Mine have been well used, so a lot of the holes are already filled up with stones that are stuck in them. But they go through the meshes, the sieves here, and and this is how they determine them or make a sieve. And this one, so here you can see the mesh a little bit better. So it's just like a fine wire mesh here, and then the sands will go through that, and we can sieve them out. So there's a whole stack of them here of different sieve sizes, and like this one here tells us that this is mesh number 35. So they have the different sizes and the meshes that we go through. But we can take those out, and you can see sort of what that sand looks like. This is fine sand, and I know it's hard to see, but if I put a ruler out here, probably wouldn't help you a whole lot. But you can see that that is what like fine sand looks like. And then we can go do some of the other ones here. Like this one is labeled as coarse sand, and you can see what some of that looks like. Is you can see how that's much coarser. There, I blew it up for you. But you can see the different particle sizes and how they sort of relate. And then also this gives you sort of a good idea too, is that if we're trying to do color off something like that, if we had some of these particles that are more transparent, translucent, the natural quartz, it'd be a little bit more difficult to do. But you can sort of see the difference on our sand and how we can go through that analysis of once we have a sample, we say, okay, this is all sand, but what kind of sand is it? Well, it's more than 25% coarse, but it's more than 50% of something else. So we'd have to call it like the fine sand because we have a lot of fine in it. But anyway, just want to sort of show you that that's something a little to be aware of when we're going through that.
Matt, I'm so grateful that you showed that. So when it comes to soil testing and sand, we often see fine sand misrepresented as a regular
Ignored would be more
ignored because
accurate.
their soil testers are ignoring it either because they don't understand that fine sand is a lot more common than is reported, or they don't want to assign a 0.5 loading rate. Both are equally bad because the system is undersized.
Right. So here I just added another sample in there. You can see that that is much bigger than what we had before. So if we had a sample like this, one of the important things for us is to identify, what exactly are we looking at? So that material that I added at the bottom of the screen here, this is a little scale here. You can see the scale on the inside is millimeter. It's inches on the outside, but you can see the little millimeters. So let me just slide this open a bit to 2 millimeters. So that gap, anything bigger than that is over 2 millimeters in size. So if I just put it near some of these particles here, you can see right there that that is bigger than 2 millimeters in size. So these particles that I all added, all these things here, here's a real big one right there. You can see that. What are these? Somebody want to chime in? I'll start calling in if somebody doesn't chime in. What are these particles? Are they sand? Are they silt? Are they clay?
Rock fragments.
Rock fragments, yeah. I said anything over 2 millimeters in size is not a soil. It's a rock fragment. It's a coarse fragment. So if we had a sample of this and we mix it all together and I say, what do we have for a sample? I'd sit there and, if I put this in front of a lot of people and said, okay, what kind of sand do we have here? Somebody would say, oh, yeah, that's very coarse sand. So that's what I'm going to call it. But until you remove all these coarse fragments, how am I supposed to know, once I remove all that coarse stuff, what's sitting underneath? That's what I need to be texturing, not the rock fragments. And so that's something also, if you work in these areas with a lot of rock fragments, a lot of sandy soils, there is a sieve that you can get that's 2 millimeters in size, that same wire mesh, but it's 2 millimeters in size. And what you should be doing is you should be running through your sample and getting rid of all of these greater than 2 millimeter size particles here and then texture what's left over. Because until you do that, it's going to throw you off, and you might say, hey, this is coarse sand or very coarse sand, where really it's fine sand with coarse fragments in it. And that's where you're going to have to make that kind of judgment call. So if we don't have to worry about, again, the particle sizes. We still have to worry about coarse fragments. You can't really sieve clay with coarse fragments in, but if you're working in the sands and loamy sands, coarse fragments, a lot of northern Wisconsin has that. You really need to have a 2 millimeter sieve in order to make those kind of judgment calls.
Hey Matt, we did have a question in the chat.
Yeah.
What sand class would ASTM C33 sand be classified as? And in the chat, I did drop the gradation requirements for
Hmm.
fine aggregate.
Yep. Most likely, it'll probably come out as coarse sand, but also ASTM C33 sand has a lot of this material in it. It has a lot of things that aren't even technically soil. There's some fine gravel components to it too, but it'll probably come out as a coarse, medium coarse sand. So once you've done the texture class, then you have to do that. Rock or coarse fragments, the percentage of those, depending on what we have, if it's less than 15%, it's just a texture only. And again, this goes for any texture class, not just the sands. So if you have, gravelly, you can have gravelly clay. So less than 50%, you just do the texture. You don't bother split anything out. If it's 15 to 35%, you do the modifier term. So gravelly sand or gravelly whatever. 35 to 60, you'd have the modifier and vary. So you could do, and they've switched this now. They just changed this that you can either do it either way. You can say, which I always thought was backwards, gravelly very sand, which doesn't make sense. But now you can actually put the modifier in front. So you can say very gravelly sand, because that's how we speak it, but that's not how they abbreviate it. But now they're allowing the abbreviation to put very in front. I should probably fix this slide to reflect that. And 60 to 90% would be extremely. So GRXS or XGRS, extremely gravelly sand. And then greater than 90%, it's no longer sand or whatever the texture is anymore. It is gravel if we're over 90%. So all rock fragments are not created equal. Gravel is 2 to 75 millimeters in size, so basically up to 8 inches. Cobbles are 75 to 250 millimeters or 3 to 10 inches. Stones are 250 to 600 or 10 to 24 inches. Boulders are greater than 24. So we had one of these reports came in. A soil tester reported he had, I think it was cobbly clay loam or something. And the reviewer said, "What is this?" And I go, "Wow, actually somebody described something correct for once." They actually described cobbles instead of just saying it's gravelly, because it wasn't. It was actually larger rock fragments. But there's a difference between gravels, cobbles, stones, and boulders. And if you want to get even more technical, if you have flat cobbles and flat stones, they are channers and flags. So you probably heard the term like a flagstone. Well, a flagstone is a stone 10 to 24 inches diameter, but it's flat. That's what a flagstone is. A cobble that's flat is a channer. So, but we don't worry about that too much. But technically, that's what they are. But again, report whether it's predominantly gravel or cobbles or stones or boulders, depending on what that coarse fragment is. So how do we determine that? Again, a 2 millimeter sieve is critical for determining what's over that 2 millimeter size. It's just a percentage. Basically, you sieve it out and you look in the pan. There's a pan underneath that catches what went through. So your soil particles, and then what sat on top of the sieve, and sort of take a look. Is it um, 35% sat on top of the sieve and rest of it went through? You can get some good ideas. But what else can we do if we don't have a sieve? Or let's say it's clay with gravel. How am I supposed to sieve that out? I can't sieve lumps of clay through my sieve. So you can do some rock fragment estimates. There's some diagrams on the left there, give you different representation. The left side is smaller, the right side is larger blocks, but it gives you an idea what 15% coverage is, 30, 25, 50, whatever. Gives you different ideas of what that percentage of coverage is. And then there's also, you could use a dot grid. So if you have a picture of the soil or something like that, you can, the blue spots are rock fragments. And so you count up how many dots do I have? Well, each of these big sections are 10, so I'm 10, 20, 24 by 21 or whatever, or roughly, well, we just ignore that. So we're 20 by 20 in these four squares, which is 400. And then how many dots do our particles touch? We had 113. So 113 divided by 400, we're about 28.5% coverage of those blue areas or blue outlined areas. So that'd be another way to do it. Well, if I don't have a dot grid, or what if I'm trying to estimate cobbles? Well, how am I going to do a dot grid out there and try to estimate, cobbles that are 10 inches across? Well, how am I supposed to do something like that? You can also do it with like a ruler. You could put like a ruler or a yardstick up and then count like every 2 inches, how many, or over 10 inches, every inch mark that I hit is going to count as one, and put it up there, do it a couple different ways. So I could say, okay, when I stuck it up there this way, I hit three pieces out of the 10. So that's 30%. I did it again. I got a 20, did it again, got a 40. So 20, 30, 40, average out, I'm 30%. That'd be another way to do it. There is a page in some of the accessory material that we have, and also in our handbook, lists what the abbreviations are. So again, make sure that you're using the correct abbreviations or modifiers, because if you report a certain letter, it's going to mean something to us when we're reviewing it, or to another soil scientist that reviews it. And stuff in the right column, if you're dealing with stuff like that, probably not a great site. That's stuff we usually don't run into and going to cause us problems. But texture terms in the middle and any kind of the modifiers, those are the important ones off of there. So physical properties, structure, what are we looking at? The structure is physically, what does the soil look like? It's its shape. So it's the arrangement of the sand, silt, and clay into aggregates or clusters, and they're called PEDs. And they're going to have distinctness of how well that we can see them, whether it's weak, moderate, or strong. Size, and it's how big, small ones to big ones, and they'll be different depending on what shape it is. And then the shape of it, what does it look like? Little granulars or crumb structure, we've had it mentioned, blocks, prisms, or platy. And then we also have structureless, like we showed you before, where it's sand. They're not in any kind of groups or lumps. They're individual particles of sand. They're non-aggregated, so it's structureless. So loose sand has no PEDs. Also, if we have a soil that's massive, and that's usually, well, it can be some natural processes, but a lot of times we'll see massive soil at the ground surface, and it's because it's been abused by human interaction or animals or something like that, where it's been compacted. But we'll see abbreviations like this, like 2MSBK would be typical. So 2 means it's moderate. and the M means size, that it's medium, and then the SBK means subangular blocky. So when we do abbreviations like that, it's usually a number, a letter, and then the abbreviation for what kind it is. So we'll sort of go and explain that a little bit. Weak PEDs are barely observable in place. A lot of times when you break them out of the PED wall or the soil wall, they will be hard to identify. A lot of times they'll break upon handling. Moderate means you can usually see them pretty easy, evident. You can handle them pretty well. And strong, there you can handle them pretty easily, very easily identifiable. They really stand out, easy to handle. So these are some sizes, granular or crumb structure. You can see what groups they break in, and each one of these are going to be different. So you can see very fine is less than a millimeter for crumb, but very fine for angular and subangular is less than 5 millimeters. So there are going to be different sizes depending on what kind of structure it is. So here's some soil structure shapes, granular or crumb. This is typically identified as a topsoil structure. Just out of convention, in all reality, subangular blocky and crumb structure aren't really a whole lot different other than granular crumb structure is a surface horizon. It's never identified deeper. If it's deeper in the soil profile, it's usually as a blocky structure.
Hey,
But in
Matt.
all reality, if you looked at them, a very, very small blocky looks like crumb structure. Yeah,
Sorry to interrupt. I wasn't watching the chat very closely. Can we go back to the section about modifiers just for a second? There were two questions.
absolutely.
Okay, so the first question was, is on the new exam, the modifiers, how are they represented on the exam? Do you happen to know if
Good
it's
question. I don't know.
okay? The meaning is the same, I
I
believe.
don't think that
That
we
section would be
actually, I
multiple.
don't think there's any questions where we specify where the modifier has to go. I think it's actually by word is that we say, and we're going to be reviewing those questions, but I think we're just asking that, if we have a sample that's 50% gravel, what would be the modifier? And that we ask something like that. I don't know if we ask you whether it's, GRVS or VGRS. I don't know if we ask that.
Yeah.
But it's
And
a good
then
question. Good question, and I'm not really sure.
the second question was regarding the 60 to 90% rock fragment,
Yep.
which requires pressure distribution in sandy textured soils. Is that only for sandy textured soils, or would that include silts and clay textured soils as well? And I dropped in the chat that portion of table 383.44.2 with the requirement for pressure distribution
Yeah,
for.
it's only the sandier textured soils, and the reason for that is you remember back at our particle sizes that when we get into gravelly sands, there's not a whole lot of surface area, not a whole lot of treatment. Where even if we are in extremely gravelly clay, because we have all those particle surfaces for the clay, even though we're extremely gravelly, it's not an issue for us.
Okay, thank you.
So, yep. So we look at these platy. These are going to be sort of basically like blocky, but they're going to be flatly oriented, like leaves in a book or pages in a book. And then prismatic. These are sort of hard to see here. These stick out. They're basically blocky, but instead of being flat and squished, they're elongated. They're tall. And you can see some here. You see these sort of the prismatic, these longer blocks. So they'll be elongated vertically. But then again, granular structure, don't confuse a single grain. You can see each one of these particles here are bigger particles. These are lumps of sand, silt, and clay together. This is what granular structure looks like as opposed to a single grain. So again, blocky, the only difference between subangular, blocky, and angular is how sharp the edges are. So this is subangular. They're sort of rounded edges a little bit. Angular, blocky, obviously to get those angles, we're going to have a higher clay content. So you usually see angular blocky is going to be more like your clays, things like that. Platy structure, here's another good representation. You can see these flat plates in here. This can be a natural soil forming process that can form structure like this, but a lot of times it's also related, just like massive soils with um, destroying the structure, is that compression or weight from equipment and things or animals can cause platy structure and sort of ruin the blocky structure and sort of deform it into platy. So a lot of times we'll see this right at the bottom of the plow plane, right at the bottom of the A horizon, the topsoil, and it's usually due to agricultural practices. So columnar and prismatic, the only difference between them is whether the tops are rounded like this or whether they're sharp or flatter. but these are going to be sort of vertically oriented, and you can see they've have like the cracks here between them, this sort of shrink swell kind of thing with the clays that form these kind of structures. Don't see them very often here in Wisconsin. They're sometimes you'll see them in the subsoil, but don't see them very often. And then again, single grain sand, structureless. They're just individual particles. They're not grouped in any kind of structure. And then massive, as we mentioned before, massive is usually some kind of compaction or other process that have ruined the soil structure in it. So a few others who want to talk about physical property, soil consistency. This is just, it relates to sort of the PEDs. It's the PED strength. Again, it's not something where we say if you have a certain soil consistency, it's either good or bad. We're going to deny it or prove it in the soil. But it's how easily they're ruptured or you can break them. So loose is like single grain sand. Friable just means, and these again have to be moist. So moist friable is you push on it, you can break them apart pretty easy. Firm takes them resistant, and then rigid is means you really have to push on it, or maybe even put it under your shoe or your boot heel and to break it on a hard surface. They have descriptions in here, and if you really want to know it's how many newtons of force have to be applied to break it, you'll just sort of get an idea of most things that we see are going to be friable, which is basically fairly easily broken. Another physical property of soil that can be identified as roots. And again, this is the quantity few per unit area, or is one per unit area. And that's going to depend on the size of the root. So if we have very fine, we're looking at less than 1 millimeter per unit area. Very fine and fine use 1 square centimeter, which is a little less than half an inch. So obviously we had very coarse roots greater than 10 millimeters in size. It's really hard to say, what's our unit area? Well, that would be per square meter, because otherwise we would have one root in 1 square centimeter. It would cover the whole area. So depending on the size of the roots, and the gives you different unit areas, whether it's few, common, or many. Again, this isn't necessarily whether if we see roots or a certain kind of roots in a certain area, whether it's good or bad, but it helps clue us into things. If we have roots that go down to a certain point and stop, then it's a concern like, why did it stop? What's going on? Do we have something like um, compaction or platiness going on here that's causing the roots to stop, or what's happening? So it's an indicator to us to what's going on, but not necessarily something we would say. Nothing in the code says if you have roots that are few, fine, and or whatever, that it's a limitation for us. Boundary. So the different soil horizons, and we'll get more into that and how to identify it and talk about those. Soil horizons are measured from the surface down. And so you'll see people that'll say under soil report, say 0 to 8 inches, and they'll do a description. Otherwise, other people will just say 8 inches, meaning that's where the bottom of that horizon is. You can do it either way, but you should go from the top down, and you don't include stuff like leaf litter or organic matter on the top. You would just include, the topsoil itself. So if there's some leaf litter or something up there, we don't include that. And then go from the top down. So the boundary, the depth is easy. The boundary is, what does that transition look like between one horizon and the next? So here we have an A horizon and a B horizon. So this is smooth, that it's basically straight across. Wavy, you can see it sort of undulates. Broken means that it's, here in one spot, not here in another. Irregular is very up and down. And then, so that's the topography, and the distinctness is how fast it turns. So like the bottom of a topsoil horizon, it's black, and then it goes to something else. Very abrupt. If it changes less than 2 centimeters, that's an abrupt. Clear means there's something here and something here, and it changes over 2 to 5 centimeters or 1 to 2 inches. That's clear. Gradual means I know something's here, I know something's here, but it changes over 5 inches. I can't really define a straight line of where that is. That's gradual, and diffuse is greater than 15 centimeters, or um, roughly greater than about, well, 5 inches or so. 5, 6 inches, something like that. So we should define what the boundary is, whether it's abrupt. So you see a lot of the plow planes are going to be abrupt, smooth boundaries for them. And so here's an example what that looks like, abrupt smooth. You can see the line. It's sort of hard to see, but you can see definitely one soil here, one soil type here, and you can see that line going right across there. That's going to be an abrupt smooth. And then clear wavy, I got soil here, I've got something here, but what does it do? It sort of does this, it changes in here, and it doesn't change as quite as abrupt, so it's probably a clear wavy, because definitely something here, definitely here, and it changes from here to here, someplace in here, so it's a clear, and it's not straight across, it's a clear wavy boundary. So, any questions on that? So, what we're looking at for soil and site evaluations. How do we handle that? What's all involved with it? Several different things that we're going to cover. So everything from fill out your profile to the plot plans, those kind of things. So as I talked about before, all our soil on-site systems are all soil based, and therefore, the soil and site evaluator does play a key role in making that on-site system work. We talked yesterday, why do you have to know about so many other things? Is that you doing the soil test or being the soil tester out there evaluating it, you're the one that lays the foundation or the base work for everything that comes afterwards. And if that is done incorrectly or poorly, it's just going to multiply. So if we have a job that's only 50% accurate, and then if the designer does something and he's only 90% accurate, well, that's only 90% of 50. It just keeps compounding any issues. Even if everybody does everything perfect afterwards, they're still only as good as the first person they're building off of, which is a soil tester. It's also important not to let owners, developers, or somebody talk you into incorrect or misleading things. I get it too as a state person. I'm sure the county people have heard it. Well, can you just get me a whatever conventional system out here? And we're not here to get anybody anything. We're here to interpret what nature is telling us it can or can't do, and then we're going to design a system that fits the site according to what those characteristics are. So we're not here to get somebody something or penalize them with anything. We're here to interpret what nature's telling us and then apply the code or apply our best practices to whatever nature's telling us. Also make sure that for the accuracy liability portion here that it's titled avoid errors due to shortcuts, oversights, or negligence. So don't, we've had some sites where people have gone out there and said, oh, I only dug down 12 inches because I knew it was um, whatever, that's all the farther I was going to go, because I knew it was going to be a shallow mound or shallow suitable soil was going to be a big mound. I didn't have to worry about that, not realizing if they would have dug another couple inches, they would have found, where the old barn was pushed in, and it was all a fill site, and it's not conducive to putting a system out there because there's bricks and blocks and other problems out there or something like that. So, I mean, don't be misled, don't do shortcuts, do your due diligence and looking at the site, looking at what the areas are that you should be, and investigating it properly. So, what's a good beginning out here? Think about where the system elevation will be, and consider the texture and structure of the soils in the pit at that location. So there's, as part of this, we do talk about that a soil tester, even though it's not necessarily your job, but you still have to know things about, and we're going to talk a little bit about some system designs and things like that, because as we talked about yesterday, if you don't know what you're testing for or what's going to happen with your soil test, are you really doing your best job out there? Are you researching the best areas? Are you digging deep enough? Are you digging the holes far enough apart? Things like that. But also, once you do that soil test, that's where the system's going to go. And if you could have found a better location or where a system may have functioned better, then you really didn't do your best job out there. So we think about things like oxygen exchange, anaerobic versus aerobic conditions. If you find a site that's shallow, that's probably better than a site that's down deeper. And of course, that gets into designers too. You can't always control that. We've had some designers say, I want to bury the system way deep because I have a better loading rate. Well, even though the loading rate's better down there, why are we putting a system at 7 feet deep? That doesn't help the system have oxygen exchange. Also about movement of water through the soil. Are there dense layers or something that's going to slow down or stop the water? A dramatic texture change? What's going on with the colors? Even locations of it, physically. I had somebody that did a soil test between a garage and a home, and nothing wrong with the soil per se. Everything tested out. They put the design in, they built it. It was a mound. And then winter came, and what happened when they had to plow the snow? They didn't plow it on top of the mound, so they pushed the snow between the house and the mound, and then they pushed the snow between the mound and the garage, and they basically created a big dam. And so when the whole dooryard to the farm melted and drained, it used to drain through where that mound was, and now it backed up and the water was a couple feet deep, started backing up into their home. They weren't happy. And also, how do you think that system's functioning when it has a bunch of water that it's holding behind it? So, not a good site just because of how water moves on the landscape. So, think about things like that. Again, deep soils not going to have much structure, if any. We're not going to have good water movement through those. We're not going to have good treatment. Sometimes leave the hole open for a while and come back, especially if you see a little bit of water or it looks moist on the sidewalls. Leave it open, or if you do an auger boring in the bottom of your pit, leave it for a little bit. Go do work in the other pits, come back, and then see, did water seep in? Did we have something occur there? Maybe the soil colors aren't indicating to us that it's wet, but I can actually see water seeping in. And then also use the soil series descriptions help you accurately describe them. We'll talk about that as going into the soil survey at the end of at the last week here, the last day. We'll talk about soil survey again and how to use those descriptions and understand. Not that we're going to be copying what's in the soil survey, but it helps us make sure that we're on the right track for everything. What are some soil limitations that we would have? Again, we talked about making sure we have our 3 foot separation. That would be above groundwater, whether it's seasonal, and that would be, you know, well, we might run into it when we're there. I mean, if you're soil testing at the time of the year when it is saturated, but otherwise, water may not be there at that time, but we'll see redox features or models or something that indicates water is there at some time during the year, or something apparent, such as, you actually intercepted the water table, or like I said, a seepage or something like that. We can actually see water into the pit, and we're actually visibly seeing a water level. Solely permeable, I mean, that could be a limitation for our design, not necessarily a separation distance limitation, but solely permeable soils, we might have to design bigger or change our linear loading rate. Also, very rapidly permeable, the high, you get a coarse sands or something like that, we do have to maintain a bigger setback distance. If you're in a coarse, gravelly sand, we may have to have a larger separation. This is 60 inches, something to be aware of. But then also bedrock, our fractured limestone or hard sandstone, or monolithic, a weakly consolidated sandstone or granite, something like that. So minimum depth of soil treatment, I just mentioned this one. If we have something like in the coarse sands, loamy coarse sands, or loamy sands, and we're non-pre-treating our effluents, so we're greater than 10 to the fourth or 10,000 colony forming units per 100 milliliters. If we're that gravelly, 35 to 60, or very gravelly, or extremely gravelly, we're going to have 60 inches of separation is going to be required. And even if we're pre-treating, if we're at 60 to 90, we're going to have 60 inches or 5 feet of separation. So just be aware, again, our separation distances, a minimum depth of soil is typically 36. Unless we pre-treat, then it's 24. But make sure that we're looking for our depths of soils for our treatment. So here's a site, bedrock limitation. We've got some course fragments up here. I guess for an exercise, if we all had a dot grid or something, we could, or if you got your ruler, you could put that over your screen and count how many times we encountered a course fragment here in a rock, and we could try to determine what these things are based on the size of the trees here. I don't know. This one is probably um, probably a boulder. It might be more than 24 inches across, and probably got some stones and some cobbles in here. Probably a lot of little small gravels. But anyway, just sort of interesting to take a look at. But these are some coarse fragments we have here. But then also, what do we see right here? Here we got solid, and this might even be up here too. It's hard to tell whether this is soil, but definitely right here, that's bedrock. That's pretty clear. We know when we hit that, we have rock. We're definitely there. We've encountered that. And then our redoxomorphic features here that we would encounter into. You can see the red blotchiness here. Some of this blotchiness, well, there's red and gray up here and blotchiness in here. And then in here, it's a little harder to see, but this is sort of grayish background, one of our glade colors we talked about. And then here's what we'd see as what they call a classic bullseye redox, where you've got the reddish orange ring around it and then the gray in the middle, and definitely clear redox features. So another one of our limitations that we'd have. And then other things to look at, we mentioned before, we're talking about, some of the structure in the soil, whether we have compaction or something going on, because obviously, all of our characteristics are based on the USDA classification system, and those all relate to growing plants. And if we can grow plants and move water for them, we can also move water for wastewater dispersal. So that's an issue for us too, is that if we have, zones of compaction or platiness, that may cause us some issue with dispersal and how our or how our system's going to operate down the road. So it is defined in the code somewhat as we have different loading rates for those. But then again, as being a soil tester out there, even though you test in an area and says, yeah, this works and this is our loading rate because we're whatever platy or we got some weak compaction going on out there, that's part of your job as a soil tester is that maybe you can say, hey, I test over there and I got out of that area and now I don't have that problem. And they can design a better system, so to speak. Want to mention also it's important to know what you're digging into. So be smart, call before you dig. We have Diggers Hotline in this state. They have a number for it. I don't know if that's accurate or not, but you can call the Diggers Hotline. And what's the other number? Was it 511 for what's the Diggers Hotline? I don't even remember now.
I don't
And it
know.
was not 911, 811. That's what it is. Yeah. So yeah, don't call 911 for Diggers Hotline. You'll get people excited for that one. But yeah, call 811 is the Diggers Hotline number, and they'll come out there. All utilities, they're required by law to come out and mark their utilities, and they will locate that. So whether it's electric or gas or cable or fiber optic or whatever it happens to be, they will locate that out there. So it's important to know. And for those that don't think about it, I've run into a couple of good stories I have for the Diggers Hotline or unmarked utilities. We were in the middle of and it was bigger than 40 acres. It was probably 60 or 80 at least, middle of a giant field. We're out there looking. We start digging down, and honest to God, 4 feet down, cable is brought up, and it's all got these little colored wires inside. Looks like a phone cable. And we're out here in the middle of a farm field, 4 foot down, and we're like, what is that out here? Well, there's no way. And the farmer's like, I don't know of anything out here. So he must not have been paying attention when they dug it in, or it was before his time and he looked pretty old, but I had no idea what was out there. And then while we're trying to figure out the rest of the site, one of the neighbors drives up in the subdivision on the other side of the woods. The whole subdivision lost their phone lines. They took everything out. So just sort of, you never think in the middle of a farm field there's a phone line running through, but it was out there. And then we had another one where it was at a campground, a county campground, and the soil tester was well known in the area. He actually had a camper there, and we were doing the digging on the Friday before Memorial Day weekend, the big kickoff camping weekend. And they had the Diggers Hotline out there. They'd marked everything off, but there was Diggers Hotline only marked the public utility. And once it got onto the property there, then they had a split in the electric line where it was considered the owner's private sort of spur line, and they hit it with the backhoe. A lot of sparks, a lot of zapping. Everybody was safe, but they blew out electricity to half of a very major campground on the day before the big holiday weekend. So he got a lot of flack for that. That all these RV motorhome campers did not have electricity for a day until they could get it hooked back up again. But anyway, call before you dig. Know what's down there. Ask questions to the homeowner. Hey, what's out here? Did you bury a line from the house out to your garage or to your barn or something that I don't know about, or Digger's Hotline wouldn't necessarily know about? Ask those kind of questions. Make sure you know what's out there. Locate the property lines. If it's not surveyed, ask the owner to mark out where the property lines are. We get that all the time where, soil test is done, stuff is dug in, and then we find out after the fact that part of the system is on the neighbor's property or something like that. And then also make sure you locate wells and not just on the proposed site, but or what's there on the property, but also adjoining lots. Find out where the neighbors' wells and things are. So that's going to be important to where you site it, because obviously, if you're digging right next to a neighbor's well and you're not aware of it, that site's not going to be suitable for a septic. So our borings, safety first. We mentioned that there are specific requirements for boring, trenching, and excavation safety. I'm not going to get into those because that's a whole separate thing with OSHA. But if you want to know what the requirements are, by all means, check out OSHA. They will tell you what's required for trenching excavation safety. But be aware every time you get into a pit, regardless of how deep it is, only a couple feet deep, there's risks of collapse of that wall. And there's been some close calls. I can say in my years, I've been buried up past the knee, and not fun. And you sort of wonder if the next wall's coming in on you, or you're going to get buried more. Don't like being in deep pits, so be aware of the safety implications of that. I'm not going to preach to you how to do your job, but just be aware there safety rules out there for a reason, and good reason. So the boring type, typically people are doing it with a backhoe or an excavator. They're digging one. You can hand dig a pit. You can also do a hand auger. You can't do a power auger. I know we deal sometimes, especially in the stormwater area, with engineers. They do a different classification, and they love power augers. They just auger down, and mostly they're not worried about what the soil looks like. They're worried about refusal, is what their favorite term is. It means they're hitting rock or something, they can't dig any farther. But I don't think they're really doing a good job of looking at anything when it gets all augered and turned up. It's really hard to identify. So we don't allow power augers. Hand auger we can in certain circumstances, and we'll talk about that when we can do hand augers compared to a pit. Soil boring location, we had some questions about that. How big of an area do we have to go, or how far apart can they be? You have to identify an area large enough to put your system in. So it depends what kind of system and how big. Is it a one-bedroom house, three-bedroom, six-bedroom? What are the soil types? That's going to make a difference. If you're on sand, you don't need to have as big an area as opposed to heavy clays. You're going to need a system that's probably 3.5 times bigger in physical area. So you're going to have to make sure you test enough area. Do have to have three observations, so three profiles to look at, whether they're pits or augers, and at least one of them has to be a pit. And we'll talk more about that and when you can do hand auger borings. And again, appropriately spaced or located. We don't have a number how far apart they have to be, but again, we're not going to approve a site where we did the corners of 40 acres and said the whole site's suitable. So we need to have the locations of the borings close to the tested area, but then again, you have to test a big enough area. Also get the question of how deep do these have to be? And if you dug a hole that's only a foot deep and you didn't find anything wrong, your limitation is going to be a foot deep, however deep you dug the hole. We'll especially get into it sometimes with conventional systems that they don't dig deep enough. They say, oh, I was good to 88 inches. And then based on the depth of the sewer coming out and getting gravity feed to a tank and then gravity feed from the tank to the drain field, time they put the system in and get it buried in the ground and still meet their separation distance. So you have to have, wherever your cell is, you have to have your cell depth suitable, and you have to have 3 foot separation underneath that. And then all of a sudden they find out that the 3 foot separation takes them down to 90. They say, yeah, but I didn't see anything till 88. Well, that's your limiting factor. That's where you're cut off. Well, we know it was good to 88. Well, what happens at 89 inches or 90? I don't know. You didn't dig that far. Maybe it changes. Maybe not, but we don't know. Maybe we've got standing water there and you just another inch deeper and you would have found it, or redox features. We don't know. So the depth of your excavation or your observations is going to be your limiting factor unless you find something up higher. So using morphology, is what we do is we look at the characteristics of the soil, the mostly the structure and the texture, and those are the big ones here. And we talked about that with the site or the soil characteristics. So by looking at structure and texture, we come up with our loading rates. And those loading rates are based on not just water movement we talked about yesterday of, just getting water off the site, but we also need treatment. So we want to make sure that any wastewater that we're introducing to that soil is not being hydraulically driven through the soil, but we also want to make sure that it has enough retention time so we get that predation, die off of viruses and pathogens. We get the contact time to adhere to any kind of contaminants that might be going through there. So we want to make sure that this is what's treating sewage. So if we just had clean water that we're just trying to move through the soil, hydraulically pushing it through the soil wouldn't be our issue. So what they call the hydraulic conductivity of soil for clear water is going to be much higher than what our loading rates are, because we're not getting rid of clear water. We're getting rid of water or dispersing water that's contaminated, and we need to have treatment take place, not just dispersal. So all of our soil loading rates are based on that concept of long-term acceptance for wastewater. So our profile descriptions that we look at, you can sort of think it as like taking a slice or a box out of the soil, and we're trying to describe vertically from top down what the depth is of each of our horizons or in our profile. And then for each of those horizons, and we'll break those out depending on various characteristics, such as a change of color, change of texture, change of structure, change in roots, redox features or not having redox features. Any change in that, it will basically describe a new soil horizon. So we'll break those out and describe those. So again, our profile descriptions: depth, color, texture, structure, consistent roots, boundary, redox features. And then if we encounter bedrock, we describe that also. Our report forms are 8330 report form. I think Katie sent that out to everybody with the initial emailing, what our forms are. So our report form, we've got the top of it here, just some raw information, to owner, their address, important things like property locations, where they're located, how to get out to that site. It's nice to report, government lot for southwest, southeast of section, township range or whatever. It's also nice to give us directions. Sometimes I have a very hard time finding these things because somebody will say, "What road is it on?" And I understand if it's a new site, they may not have a fire number or something, but I'll have somebody say it's on, whatever, Smith Road. Well, Smith Road is 6 miles long, and I have a hard time trying to figure out where exactly this 2 acre parcel is along Smith Road. Even with the township and range, I can sort of narrow it down a little bit, but it's a lot easier if you write in there and say, "Hey, it's on Smith Road, but it's exactly, 3/4 of a mile from the intersection of Smith Road and County X," or something like that. So it helps to put a good description of where the property is located. Some other things here, whether it's new replacement, things like that, some generic information. And then here we'd start filling in, like pit or boring one, and then all of our information, the horizons, the depth. And we'll talk more about horizons. If you don't know how to do the nomenclature form, if you don't know the difference between an A horizon and a B horizon or E horizon, and we'll talk more about that later. Don't worry about it. You can just report horizon one, two, three, four. That is perfectly fine. If you're not 100% sure of what the letters and numbers mean, don't put them down there, because if you write a B horizon to a soil scientist or to the state, it's going to mean a certain thing, not just necessarily the second horizon. The third horizon isn't C, the fourth isn't an E, fifth isn't a D. They're not in order. They actually mean things. So if you're not familiar with it, by all means, don't put those down. But otherwise, we'd fill out, our depth, our color, redox if we have it, texture, structure, consistent boundary, roots. And then based on that information that we have in here, mostly the structure and texture, we would then assign our loading rates. So make sure you use your proper abbreviations. They're in the Soil and Site Evaluation Handbook. They're in the USDA Soil Survey Manual. Don't dream up new things or write things that don't make sense. And if you have something that's an oddity or something that you run into, written narratives for special conditions, by all means, write that up and let us know. If you have a soil that has like some banding in it or something, every, for the next 2 feet, I've got whatever 10YR, 6/4 loamy sand, and I have bands, 1 inch bands, approximately every 4 inches of something else. You could write that description in, or you don't have to write out every little 1 inch band. You'd have 40 different horizons. You don't necessarily need to do that, but we'll talk more about that. But if you have a written narrative or something that's special to note, by all means, write it out or narrate it to us. And if there's nothing to report, put a line in a box. If there's no redox, put a dash. If you have roots here and then a root stop, just put a dash in to say that, you know, I've otherwise we think that you're incomplete, that you didn't evaluate it, or we're wondering, is there anything there, or did you forget to complete it? So if there's nothing there, just put a dash. So when you go out and do the soil and site evaluation, make sure you have the proper tools. Munsell color book is a must to do the colors. We say a knife, but a lot of people We'll get some kind of cheap, heavy duty knife like the Rambo kind of style knives, a real heavy blade to poke around in the soil. I know other people will use like a trowel for like masonry trowel or something. I've in the past used a real stiff putty knife or something like that. So you can find, it's basically something to dig with. I know one guy he used for years a big jumbo flathead screwdriver, and that's what he poked around with. But just something to dig with in the soil profile. You need a tape measure. It helps to have a short one for inside the pit. Also helps to have something longer, maybe like a reel tape, 100 foot long tapes to measure distances to like a well or property line or something like that. A water bottle, not just for you if you're thirsty out there, but for the soil. If the soil's dry out there, you may have to wet it. A little spray bottle. You can find them at the dollar store for a buck a lot of times, so you can mist it, spray some water on your sample. A notebook or some kind of clipboard in order to take notes. So you can have your field notes if you want to take the form and fill that out. That's great, but you may want to just take some other notes down too, or something to sketch like a plot plan or something out on. And then some kind of surveying equipment. You'll need either a builder's level, laser level, or some people now are going to like a total station or survey grade GPS. They just go out there and gathers the data for them, and they go back to the office and computer will generate them a map of where they were at. But you will need to have some kind of level out there to or something to take elevations so that you can locate where you are. It doesn't hurt to have some flags, little wire flags or something to mark out locations of. I know a lot of soil testers, or several soil testers in my area. They will have flags that they'll mark out the location of where they did the soil test, or where the estimated contour line is, or where the estimated corners of the cellar is going to be. And then, like a tiling spade or a sharpshooter is what we call them, the sort of the narrow shovels, or you can use a regular shovel, doesn't matter, but something to dig with if you need to do a little more digging than what your knife or your putty blade will do. And then a soil auger. So you may need to either auger a different boring someplace, or even in the bottom of your pit. Sometimes you want to go down deeper, but you don't want to be standing in a 10-foot deep hole. You can auger down a little bit farther to see what's down below. So part of the soil and site evaluation components, what are we collecting out there when we're on the site is some soils data. It's the reason we do the soil test is very site specific. We can look on a soil survey and get the general idea of what's out there, but we're not necessarily going to know exactly what's in that area that we're going to be putting the septic system. So it's very site specific. You can get a soil survey to get you an idea what's out there. But even when you look at the soil surveys, or which we'll do next week, they give you an idea. But sometimes you'll look up things and it'll say it's 80% this, but 15% this and 5% something else. Well, to us, it may make a difference if it's that 5% or that 80% may make our designs. So we have to specifically look what's out there. And even on the soil survey, they may say water table at 3 to 5 foot. Well, it makes a difference for us if it's at 5 or at 3, or 1 to 3 foot is water table. It makes a big difference for us. We need to know exactly what's on that site. And then permeability, we get the loading rates from the code again based off of the texture and the structure. We'll determine what that long-term assimilation or long-term acceptance rate is for the soil. And then we gather, besides the soil data, the profile descriptions, we also have to gather site information. So a vertical and horizontal control basically will set a benchmark that we'll survey back to. Locations of features and other encumbrances. So if we have a building that's in our way, or a driveway, or a property line, or a well, or a river, lake, stream, things like that, that we have to maintain our setbacks from, we have to locate those and describe them and accurately map them where they are. And then also land surface slope and direction. We have to do contours or show elevations of the site. So the soil data, the site information, plus our code requirements gives us sort of the roadmap for the designer to determine what they can put out there and what they can install, and then to build off that, to put that design on paper and go from there.
Hey Matt, can we go back to a few other things that people in the chat
Oh,
bring
sure,
up?
absolutely. Jump in right away. You guys can feel free to just ask the questions. You don't have to chat. You can jump right in if you
Oh,
want.
so these are just two
Uh,
suggestions from two working soil testers, I guess I would say.
yep,
So it's some additional things that they bring, being nails and ribbon and a hammer for the benchmark if you're
yep,
nailing ribbon and nailing and ribboning off a tree. some people, I know there's one soil tester in the Chippewa County area that he nails a Mountain Dew can into a tree. It's not the most aesthetically pleasing thing, but when he's been out on the site.
Well, you'll see it. Yes. Yep. Yeah, that's a good thing for the benchmark, and we'll talk more about that, establishing good benchmarks. But that the reminds me of that is that a lot of people, if it's an undeveloped site, I mean, if it's a developed site and they've got like a, the back porch corner of a slab or step or something that's concrete, not going to move, you can use it as a pretty good reference point. But if you're on an undeveloped site, you're going to have to try to find your own benchmark or put one in, such as a nail in a tree with a ribbon or something like that. And that reminds me that, yeah, nails are good. And it's also, I've seen people use nails or colored ribbon or something like that for even in the soil profile. So instead of trying to remember where you had different horizons, some people will stick nails in or something to mark, here's the bottom of this horizon, here's this horizon, and so they've got some markers that they can actually stick in the pit wall to identify
Yeah,
things.
that was the second suggestion in the chat, and it does make it a lot easier to visualize, especially if you're having diffuse boundaries, like where it actually
Yep,
is.
yep, good points, good points. So as you do this, everybody will have their little nuances or little tricks that they will use, out in the field. So here we have some when we're looking at a site, again, as use a soil tester, you have to pick an area. Where am I going to go? Where am I going to do the soil test? And you have to be a little bit smarter than a homeowner. Sometimes homeowners say, "Hey, I just want it right out the back door." Well, if the back door is this top middle picture right here, do you think that's a good area to maybe be doing a soil test? As soon as you kick Bossy out of the way and tell the cows to move and you do a soil test, is you think that's a good site to do a soil test on? What do you think you might encounter for some problems there? Anybody want to jump in? Anybody? Anyone?
For the group
Oh,
compaction.
it's compaction. There you
Yeah,
go, Katie.
reading it from the chat.
Yeah,
Compaction.
compaction. So if this is right outside, it's not much of a barn there, but outside the barn, maybe they've been doing feeding operations there. They got cattle there compacting the soil. Maybe that's not a great area because it's not natural. It's been impacted by man, whether it's just the animals there or whether he's driving a tractor into the barn or something like that. I'm envisioning there's another building just out of frame that they've compacted that site. Probably not a great idea. So site clues can give you some things. The cow is standing there. That's a pretty good site clue. Land use history. What have they used that for in the past? What about the upper left picture? Anybody besides Katie want to chime in? Anybody know what that is? What is that vegetation that we see out there? Anybody got a good idea?
In the chat, we had a comment that it's
Okay.
wet.
It's wet
Dogwood is
because
wet.
it's red osier dogwood, which is a wet indicator. So yes, if you have vegetation and you're looking where to dig, I mean, obviously you'll probably figure that out once you dig a hole and you go, well, this isn't very good over here. But you'll use those clues when you get out to a site. You'll look around and go, well, I'm not digging over there because I've got wet indicators. I'm not digging behind the barn. That's not a great one. We have in the upper right, we just have land use history, field margins. They haven't been plowed in 30 years. They're really cloddy kind of thing here. It's maybe not a great location. Headlands where they're turning equipment, or I'm not going to test and put a mound right at the entrance to a field because I've been going through that gate with tractor after tractor or hay wagon after hay wagon. It's probably pretty beat up. Even though you could test it and get a loading rate and maybe get a system there, it's not a great site because it's been beat up. It'd be better to move over to a more natural area. So now we got a picture in the bottom there, the cornfield. What do we think's going on there? Anybody want to jump in and say that? Or you can type in the chat and then Katie can say it for you. What do we see here?
So the chat says it floods. There's possible past evidence of water. It's wet.
Yeah, we've got corn here growing really
People
well, and then
farming.
we've got the corn is sort of yellow and died out in here, bare patches. It's probably wet. This is a depression that's probably holding water. So not only are we in a collection area, which isn't a great place to put a system, but it's probably going to be pretty wet here, may not even pass. And if it does, do we really want to build a system here where it's receiving water from all the neighborhood and dumping on top of that? It's not a great location. So again, using the site clues to sort of key us into, what areas should we be looking at? What areas should we avoid? And then as time goes by, you'll get a better idea that, yeah, don't even look there. Or if we, maybe that's the only spot and we have to try to shoehorn a system in. but it isn't great. It isn't going to work well. And you can look at those site clues to sort of key you in. So here's another picture. What do we see here? Well, we've got these big lumps, and in between, we've got sort of these dead spots. This is what we call a cradle and knoll topography. And this can indicate wetness, as we will have water sometimes sitting in these here and be higher ground here. But we may have no suitable soil here. It's wet. And then up here, we maybe have some, not a great site when half the site is, quote, dry enough and the other half the site is wet. It's going to be rough to work because you're going to have to bring in a bunch of fill in here, even if we would allow it, which may not, depending on how bad this is, fill in here to up to the tops to try and do something. It's a really difficult sites to work with when we get this cradle knoll topography. This one doesn't show it too bad, but a lot of times when this is really wet, you'll see the trees that will have really wide along the bottom of the stumps because they're buttressing. They're real thick at the base of the trunk, and because they're trying to hold themselves up because it's so wet, the trees do that so they don't tip out of the ground. And maybe that's where some of this is from, is old trees that have fallen over, the root balls come up and leave these lumps and stuff out there. So indicators that this may be a wet site, a problem site for us. So here's one I was just mentioning about that. You see how this tree comes down, and then when it gets towards the base, how it gets so wide here, it's trying to buttress itself up. Well, why is this tree doing this? Well, it's hard to tell, but this is actually a black ash. And when you put the word black in front of things, usually indicates wet. And you can also see this grassy sedge vegetation here. This is pretty wet stuff. And then what's our soils look like? Well, you can see the standing water in it. And this is gray up above. We have it listed as A and a BTG. This is G. These are glade conditions. We talked about that glade page. It's pretty wet conditions means water sitting there all the time. Yeah, because here's where it is today, and in spring it probably comes up probably close to the surface or above the surface, I wouldn't doubt. So yeah, it's a very wet site. But before I even dig the pit, I can see this tree here and see the dead vegetation here and this kind of vegetation, and have a very good clue that this is probably a pretty bad site, pretty wet site at times of the year. Want to mention floodplain issues. So floodplains come sort of in two categories, the floodway and flood fringe. Both of them together make the floodplain. Sometimes these are defined differently, the floodway and the flood fringe, depending on how much work has been done in that area, whether it's mapped out or not, or if it's just all considered floodplain. They may not describe what's the floodway and the flood fringe. But our code, it ties in with the DNR code, says you cannot install in a floodway, and it prohibits installation there. There could be a replacement installation if no other alternatives are available, and typically that'd just be a holding tank. Um, we do allow installation in the flood fringe if the components are flood proofed. But again, this is going to be something you're going to have to talk to the county on, get some information on elevation data needed at what the floodplain is, and the flood proofing we have to know because a lot of our code refers back to has to be either like a vent pipe has to be 2 feet above the regional flood elevation, or it has to be flood proofed. And so we'll need to have those elevations at how high the flood gets here in relation to your site information. So it's best just to stay out of them, but if you have to deal with them, probably best to contact us and we can help walk you through that process. So area requirements, even though you're not doing the design, you have to know as a soil tester, you have to have a basic knowledge of what kind of system is going to go out there and the design of it. If you don't test a big enough area, again, you're not going to, whoever gets that after you isn't going to be able to design a system out there. Or they're not going to be happy. They're going to ask you to come back out there and do some more work. So what's out there? Do we have fill? Do we have groundwater, backfill material? What's needed? Residential commercial sizing, may be significantly different. So you have to be familiar with how to do that commercial sizing chart. And then gravity versus dose systems. If you can get gravity flow, that's very important. If you have a house on a hill, you probably want to be testing downhill where you can get gravity flow. If you test an area that's up the hill, not to say you can't do that, but then you're going to have to make sure the homeowner is aware that, well, we can put it there if that's where they really want it, but then you may have to put a pump out there, pump tank. It's going to dose. It's going to be more expense. Things are going to change. So it's a cost factor. But sometimes that's maybe the only place to go, or that's where they want it. They don't want it in the backyard or whatever, or down the hill for whatever reason. So just a little joke in here, describing the first dirt molecule. But this is part of our job as being a soil tester is to describe what we see out there so we can convey it to somebody else and they can take that information and build off of it. So soil variability, here's the map. We looked at some of it yesterday with the soil forming factors and what the soil maps look like. But there's you know obviously different parts of the state have different soils, and even within that, soils will have some variability. And even what the soil survey says, even on a site, like I said, sometimes you'll have them where it'll say, it's a certain percentage of this, a certain percentage of something else. Even if it doesn't say that, it says this is a whatever Casco soil. Even within that, there may be small inclusions of up to a half acre or an acre in size of something different that they can't map out every little variation. So that's why we have to do a soil test specifically for the area under investigation. So within our area, what are we looking at? We're trying to determine the depth and elevation of what our limiting factor is, whether we encounter something or just the depth of our pit. We're trying to determine permeability to not only water or long-term application rates, but also air. We want to see, can air get into that system or not? Our influent application rate again ties in with the permeability. Not only where is it going to go, but what are we doing? How many gallons per day are we loading it at? Rock fragment content. Do we have rocks out there or not? And do we have to do something different? Might tie in with our application rate and topography. What the lay of the land is, the slope. We want to make sure that we're putting it in a good location so that we're getting good drainage, not receiving input waters, things like that. So, as a three-dimensional soil, we're looking at that profile as a piece out there, and we're trying to determine that and extrapolate that out to the whole site. So the important thing to remember is that we're only looking at one little, whether it's a pit or an auger boring, we're looking at one little slice. And so this little cartoon is just to sort of give you an idea that if you had a blind person that could not see that it's an elephant, and you had the guy in the front said, "What do you think you're touching?" And he puts his hand out and pokes the tusk. He said, "Oh, it's a spear." Or it's something sharp. You get another guy sitting up on top and he feels the ears and he goes, "Oh, it's a fan. I'm getting a draft." The other guy is touching the trunk saying, "Oh, it's a snake or something." And another guy touching the leg and saying it's a tree. Another guy touching his side saying it's a wall. Another guy touching his tail saying it's a rope. I mean, it's a cartoon, but the idea is that if you're only focusing in on one little spot, even though we're doing the profile in one spot, we need to look at the area and make sure that that profile is representative of the area that we're looking at. We can't hyper focus on what we're seeing here and can't miss the forest for the trees kind of thing. We have to be able to identify the whole picture, not just what we're looking at. So, a point of observation. So, if I got my profile and I describe this profile right here, am I 100% confident of what I'm seeing is truthful? Yeah, for right here. But I didn't dig the pit over 3 feet to the right or 3 feet to the left. What's over there? It could change. I don't know what's over there. I'm pretty sure if we know how soils form and the soil forming processes and things like that, that I have a pretty good confidence interval around that pit that or that profile observation that that's what I'm describing is what's in the area. Now, 3 feet away, pretty confident. 5 feet away, still pretty confident. 10, yeah. 20, 30, 40, 100 yards, a mile, 10 miles. Well, obviously, 10 miles away, a lot of stuff could change. So, someplace in there, it's going to change and not be the same. So, we have to look at, what's our variability from that. So, we have vertical variability in a profile. Things change as they go top down, obviously, the topsoil to the subsoil to the parent material down at the bottom. But we also have that horizontal variability. So, that's why we test out we talked about it, test out an area. So if I did these four borings here, the dotted line is sort of my suitable area. This is my area of confidence. I've tested this, put them here. If I put a system in the middle here, that's my area of suitability. What happens over on this hill point over here? I don't know. What happens over on this side yard? I don't know. That's outside of my tested area. So the important thing is to be aware of horizontal variability among the borings and figuring that out. Soil boundaries, not going to get too much into that. There are a little bit of variability too. Not going to worry too much about it. We're sort of a little bit short on time here, spending too long. But 385 requires that at least three profile evaluation excavations shall be used to delineate a site. So you have to have at least three. The issue we run into is that if we have three, that makes a triangle, and we're putting a square system in a triangle. So we need to make sure the majority of the system is in that triangle. We don't want to put them so close and have you know 50 feet sticking out past our tested area. We want it to be in that tested area. So if we test out there, we can do our profile descriptions. We only have to have one pit. The other two could be bucket augers if we wanted to, soil augers. Now, the key for that is whatever we see here has to be the same we see in the bucket auger. If we dig the bucket auger and it does not look like this, then we're going to have to dig another pit. So they have to be the same. We're just basically digging those two auger borings to verify what we see is the same as what we saw in our pit. So if we're greater than 1,000 gallons per day, we have to have three profiles evaluated as soil pits. So under 1,000 gallons, based on resident, 3-bedroom residence, we typical. We could do one pit, two borings. Greater than 1,000, we have to do three pits. But then again, that variability on that, we have to make sure that whatever we dug matches up with what's beyond. So here's an example. If a pit, sort of confidence intervals and getting into some of the math and probabilities and statistics, is that we're probably pretty confident, if we got a 6 foot long pit, we probably got a pretty good confidence that, that confidence interval, 6 feet around that pit, we're probably pretty confident that we know what we looked at. If we're two distances or two standard variation units beyond, 12 feet away, our confidence is sort of, maybe. And if we're three distances away, 18 feet away, like I said before, what's really going on out there? Probably not so confident. So why do we not do one pit? Well, because we don't know that confidence. So if we did two here, we sort of got this dumbbell kind of shape that I'm confident in my circle around here, confident in my circle around here. This pit looks like this pit. I can probably have some confidence that what's in between it, as long as I'm not like, 100 yards apart, that my sort of two zones of confidence sort of intermingle, make a dumbbell shape. And then if I do three, I got one pit, two pit, three pit. I've sort of mapped out an area here based on the contour elevations where my pits are. I've got a pretty good, sort of the multi dumbbells tying in. I have a zone of confidence. And so this would be my zone of confidence or my tested area. That's why we don't just draw a line between the pits. We allow it to stick out a little bit, that, we understand that this is sort of the tested area. If we put a cell in here, that is our tested area. Sort of gives us our 3D dimension kind of thing of um, of reliability. But it would be best to do a four-hole one, two pits up, two pits down, and now we got a nice square. Again, trying to put a square system in a triangle is hard to do. Square system in a square is a little bit easier. But then again, code doesn't require four; it only requires three observations. But this would be a much better job again. And then if we really wanted to do it, not only did we test out an area, and I know a lot of people do this and they don't show it, and you really should show in a soil test, or at least on a plot plan, say, hey, I did pit here, pit there. These are bad, or these don't show. This only shows whatever 6 inches. This shows 18 inches, and this one shows 30 inches, and that one shows 32. And I found a better area, and I cut these, by putting this good boring here, I sort of cut those bad borings off. So sometimes it's not bad to have other ones out there that show bad areas, to know that, that's not a good site. And I've very well delineated what's good and what isn't. I know this is good because I've already identified that's a bad area. So determining system elevation, again, separation distance, a limiting factor. Do we have coarse fragments? Are we doing pre-treatment? We only need 24 inches instead of 36. We have these things called tension saturated horizons. We'll get into that later. But where we determine our system elevation, our loading rate is at that system elevation. So the topsoil may have a loading rate, but if our system is 2 feet deep in the ground, the bottom of our system is going to be at 24 inches. We have to take or determine what our loading rate is at that elevation. Also,
Maximum
our
in
yeah,
the chat. Okay. Is there a requirement in the code for maximum distance between borings and a proposed system? Which is
no,
the
there is not. There's nothing in
elephant
the
in the
code.
room question all the time. So,
Nope, there is not. It's a judgment call. Again, as I mentioned yesterday, we need them to be near the system or in the system area that you're proposing. If you did four borings on the corners of a 40-acre lot, we would kick that back and say you did not test the area. It doesn't make four borings into 40 acres does not make the whole 40 suitable. We need to know in that area. So I don't have a really hard and fast number. It also depends on what the soils look like. If the soils are very uniform, not changing much, and very deep, probably not an issue. If you're 12 inches in one pit, 32 in another, and 98 in the other pit, and you've got them far apart, I'm going to sort of question you know, where you're putting that system and what's going on. We may ask for additional information out there. So it's a judgment call. I know it's not a great answer. It's probably something, different than what you'd like to hear. But as you're doing this, you'll get the idea of how far apart you can have them or if you're a county and you're asking that question because you're having problems with somebody, let us know. We can take a look at it and discuss that, whether they're in fact covering an area or not.
okay. There was a second question in the chat regarding sidewalls or necessitating them to have the same loading rate, I'm assuming as the infiltrative surface in it. So I could speak a little bit to that, in that some product approvals, especially in the past, had more restrictive requirements about, if you're receiving certain credit, then this should be on the sidewall. But as far as I know, the product approvals don't include that language anymore.
That's correct. It's the infiltrative surface, and so it would be the bottom of that cell.
But you have to, keep it in mind that if you find 0.7 sands underneath massive sandy loam till, probably should put the entire
Or in reverse, just
circle
like the
cell
fourth,
in the sand, not, 1 inch.
right. But just like the fourth bullet point here, loading rate in the treatment area uh, the design shall reflect restrictive soil horizons. So I had one where they wanted to put the system elevation in, which was in sand, a zero point 0.7 loading rate, but literally 1 inch below that, it turned to virtually massive clay. And I said, well, how are you going to load it at zero point 0.7? Then 1 inch later, you basically have a loading rate of zero. Where's that water going to go? So again, they'll have to take that into account as part of the design. But things to also look at as you're doing the soil testing when you're running into it to make sure we're calling out stuff like that. It does say here the fifth bullet point in situ soil on the sides of a system. So that relates to product approvals is that even though the infiltrative surface is what we base the loading rate off of, we still have to have, even though loading rate may change, we still have to have natural in situ soil to the sides of the system. So you can't just bury a system 1 inch into the ground, a conventional, and then bring fill in around it. The whole dispersal unit or the cell has to be in the ground and have natural soil around it. So we're going to look at things like this. We talked about some of this before. Where we determine our high ground or our bedrock or our limiting factor, make sure we have our vertical separation distance, room for our system, room to cover it off, or we have to bring in some extra fill. So this is what we're trying to do out here is that we have to keep this in mind when we're doing our soil test, where we're at, what the system's going to look like. So minimum depth of soil treatment, we've seen this before, we're seeing it again. Make sure that we have our depths of suitable soil because you don't want to go out there and if you only tested a few inches and then realize that, or the designer realizes that, hey, we needed 60 and you didn't test deep enough, that's going to cause them some issues for their design parameters down below or down the road. And then our soil application rates, again, whatever we have, let's say a loam. So if we have like, let's say a blocky structure, subangular, blocky, or angular, and it's moderate in grade, then we'd have a zero point 0.6 loading rate for non-pretreated effluent. And if we're doing pretreated effluent, less than 3030 here, BODTSS, then we could load it at a zero point 0.8 gallons per square foot. So it makes a difference on what we test and where we're at. Again, if you have some sites out there and there are different textures on one side of the property to the other, and it's not going to make any difference which way we pipe it out of the building. Those are some things to explore when you're out there to see where we can get the quote the most advantageous loading rate, which means a smaller system means less expensive for them. So more application rates, just the rest of the table here, and you can see a lot of these, like if we have sandy clay loam or silty clay loam or clay loam, and it's massive, we have a loading rate of 0. We're not able to apply any wastewater to that. So just be aware of those limitations. And then our sizing here, um, how do we do our sizing? So it's our design flow rate divided by our soil acceptance rate. So for example, three-bedroom home, again, you don't have to be a designer, but you have to know a little bit about it. Three-bedroom home, 150 gallons per bedroom. So 3 times 150 is 450. That's our design rate. And then our soil acceptance rate of, let's say we have a zero point 0.5 based on our texture and structure. So we take 450 divided by zero point 0.5 means we need 900 square feet of absorption area. So way to do it would be two 5-foot by 90-foot cells. So when we were talking before about what area do we need to test, well, if we're doing a 5-foot cell, we have to maintain 3 feet between the cells. So 5 foot plus 3 plus 5 foot means 13 feet wide and 90 foot long. So we have to make sure that we have, borings in distances. So maybe a boring here. We have to do borings at least 90 feet apart. And then we have to probably do them at least 13 feet from here down to here to make sure we have room to put the cell in, that we've tested a large enough area. But then again, we don't want to have a boring, way over here, 100 yards away and a boring over here 100 yards away. We're not testing the area. So for instance, if this is what the first pit looks like, we should probably be testing one here to define our area. So EISA calculations, these are used for things such as chambers. They're a little bit different. So first of all, we determine our design flow rate, 450 gallons per bedroom, determine our application rate, just like we did before. Soil application rate was SAR. And then, so just like we did before, 450 divided by zero point 0.5 gives us 900 square feet. But then for any of these products like a chamber, like Easy Flow, something like that, they will have a EISA rating number for them. So this one has 25 square feet per unit, whatever that is, a bundle or a chamber or something. So we take our 900 that we calculated before, divided by 25, tells us we need 36 units out there. So once we have that, we choose the system, consider our loads and flows, determine what kind of systems out there. Obviously, if you only have less than 36 inches, we're going to be a mound. 36 to more, you might be able to get an at grade. And then if you have enough room to fit everything in the ground, like 60 inches or more, we could do a conventional. So septic tank, effluent or pre-treated effluent, area, slope, permeability limits, whether it's a below grade or above grade design. And this looks at like a mound cross section. So again, when we do our testing here, even though this loading rate of the ASTM sand up here is only 1.0, so if we had a 450 gallons, a 3-bedroom system, we'd need 450 square feet of area up here. So like a 6 foot wide by 75 foot long. But we also have to compensate the mound itself, the fill around it. We don't want to have soil pits in here in the mound area. Where we're trying to get treatment, we're going to short circuit. So we want to make sure we did our test pits outside of that mound area. So something to be aware of is that even though you don't design it 3-to-1 slopes, once we add our fill depth, it's our limiting factor. So if we have 12 inches of limiting factor, we're going to need 24 inches of fill, foot for cell, foot for cover. That's 4 feet roughly, figure 3-to-1. We're going to need an extra 12 feet around that system area, give or take. And there's calculations to get more correct, but we're not doing the design, just giving you some ballparks. But the other important thing too is that basal area. So under here, this basal area, so the cell and directly downslope of it to the edge of the toe in here, this basal area has to meet our application rate of whatever our topsoil is. So if our topsoil is a zero point 0.5 application, even though they're designing this at a 1.0 for the sand, this whole area has to have a 0.5 loading rate. We need to make sure that we have enough suitable soil. So they'll get into the design for that. But again, what you have to be aware of is if you have a surface horizon with a very low loading rate, this is going to be a lot bigger. You're going to have to make sure you test enough area. And then also linear loading rate. If we have in situ soil with a point 0.3 or less, they're going to have to do no more than a 4.5 gallons per day linear loading rate. That means they're going to be putting in 4.5 by 100-foot cell for a 3-bedroom mound. They're not going to do a 6 by 75 or a 10 by 45 or something like that. They're going to have to stretch that out. And then commercial sizing, this is where it gets a little more difficult. Have to find out what they're doing. Um, so patron seating here, um, you know, restaurant with toilet kitchen waste, 40 seats times 22 gallons per patron seating is what the table says. 6 employees at 13 gallons gives you a total of 958 estimated flow. And then we multiply that by 150% to get our design flow. So just be aware, we have that in there. How big the sizing has to be, but then also be aware, not so much for you, but then, the designers have to be aware that that's probably going to be high strength waste and a whole nother issue. So the question is here, are you testing a sufficient area and in a good location? So in here, we have the three borings here. They're spread out. We've got a tested area. The majority of the cell, the proposed mound is in the tested area. Do they think we did a good job on this one? Yeah, it looks like pretty decent. They tested a sufficient area. Does it look like a good location? I don't know what the soil report is, but I assume it's okay. But that's the thing here is what is this, for the soils as far as the locations are. I think they did a good job. They marked out the benchmark here, the corner of that shed. We've got a plot plan. We've got everything listed out, address and everything. We've got a good map of where the buildings are and the sheds and the barns, driveway and stuff like that. I think they did, the plot plan looks good. Are the soils good? That I can't answer without looking more. But site plan has to clearly indicate to someone who hasn't been there exactly what's going on and all the features for that. So make sure that you're thorough. So by following this, I can see, yeah, okay, here the road driveway comes in from, this area here, and I can see where all the buildings are. I can see everything laid out. It's very clear to me to what's going on. The house is here, tanks are there, drain fields there. Should be able to follow that map and be very clear. Because you got to remember when somebody's reviewing this, I haven't been to the site. I'm not familiar. I don't know what's going on. So components of a good site plan, use a good compass to determine north, or if you're mapping stuff out, make sure that you're orienting things. Every once in a while, I'll get one in where they put, they drew it from one direction because that's the way they were facing off the road, but north isn't up on the map. It was sideways or something, and I get out there trying to figure out what's going on, and then realize north is different direction. Try to get north oriented north or up on the page. Scale drawings of 1 to 20 or 1 to 40 seem to be best. If you're doing a small plot plan like this, and your scale is 1 inch is 1,000 feet, it's going to be so tiny we can't see anything. Also, we don't need super detail. I don't need 1 inch is 1 foot because you're going to have a giant piece of paper to get everything on it. So you need to have 1 to 20 or 1 to 40 is best. 1 to 40 is pretty common. Describe the benchmark, not only horizontal but vertical, and it has to be something permanent. Don't use grade. We've broken most of people's habit of, grade at base of tree. Well, remember that picture of the tree we showed where the root, the trunk kept widening out, and exactly where did that meet grade? I can't determine that probably within 6 inches. So really hard to do. I know some people use center line of road. Well, where exactly is the center line of road? Where is, even if I found the center line of the road, I could see where the left lane and the right lane seams came together when they, put the asphalt out there. The problem is left or right exactly, where is the spot that I'm trying to determine is the point. I got the center, but I don't know, left or right up the street which way I'm at. Also, setting an alternate benchmark isn't a bad idea, especially if it's an undeveloped site. If you're out in the middle of a field and you set a benchmark or your tree, that benchmark can get destroyed, and it doesn't hurt to have another benchmark in a different area that's protected. So this is where I'll tell one of my favorite stories. I went out to review a soil test, and it was a really bad description. It was a pine plantation, red pines, and the site was on like a 160-acre block, and they gave me some rough directions, approximately 400 yards off the road. And so here you are wandering around a pine plantation, red pines, looking for a site in the middle of a pine plantation about 400 yards off the road. So I'm wandering around out there trying to find it. And I'm looking for a nail in a tree. So remember, we talked about our nail in a tree with some pink flagging tape on it. Well, after wandering around, I finally found the nail in a tree with the pink flagging tape, could locate the site, looked at it, everything looked good. Fast forward to next year, the county calls me and says, "We got a problem out there. What's the problem?" Well, what do you think they did with a whole pine plantation and they were going to build out there? They cut down all the pines. So, what do you think happened to that nail in that tree in the middle of that pine plantation? It was in one of the logs sitting there waiting for the logging truck to come to take to the paper mill. Everything got cut down. So what happened to your benchmark? It's somewhere in that pile of logs and they lost it. So, be aware of especially something like that if the benchmark might get removed or destroyed to put a second benchmark or try to protect it. Mark that tree and say, leave this tree. This is my benchmark, that kind of thing. Indicate percent direction of slope, neatness and legibility, do count, use a ruler or use some kind of drafting program or even Microsoft Paint to draw stuff out. We've had some terrible plans come in, terrible handwriting, terrible legibility we can't see. Don't copy things. We've had some people use air photos as a base layer and try to draw on top of it. It gets too dark, too cluttered. We can't see. It should be a clean sheet like this one so we can see everything. If you had an air photo as a backdrop on there, we lose all the lines. We can't see stuff. Don't extend contour lines beyond your data points. Label things like property lines, piping. Too many times we just see lines on there. We don't know what it is. There's a building with a line with a square with a line. What is that? Oh, that's the building sewer and a tank and another line. Or is that a fence and a shed in the middle of a fence? I don't know what that is. So make sure we label things. Benchmark, permanently established point, elevation is known, or we assign one. And it's also a horizontal reference point where we can measure back from. So things like this, you can use aerial photo for supplemental information to sort of map out the site, but don't use it for a site plan. If I start drawing on here, this is where my pit was and where my lines are, we're going to lose them, not be able to see that kind of detail. So again, we saw this picture before, site plan, scale drawing, horizontal, vertical, grade elevations. If you had surface water, mark what that is. Locate your borings, buildings, property lines, utilities, area for a system. We've been having some issues about what's a suitable area. We recommend putting a dotted line on and calling it out, saying, this is my suitable area. Then there's no argument about, if I got 3 pits here, does that extend? If I want to put the system here, that's good. But if I want to put it over here, is that still suitable? Well, if I dotted the line, then I know that's a suitable area. Want to mention a little bit about public land surveys and how that works with our legal descriptions that we have. So the public land survey system, the way it worked is Congress wanted, a survey of the land. They wanted to know what's out there and to have some way to differentiate between, my acreage and your acreage. So they sent survey crews out in the 1800s in Wisconsin here, earlier as you were east and later as you went west. But they had crews that were out there and they surveyed and they did it with a surveyor chain. And that's what this looks like here. It's actually a chain made up of these long links and they actually physically stretched it out. They had a compass and a surveyor's transit, and they physically mapped out the areas and they put survey markers like at the corner of like sections and things like that and physically map stuff out. I think it's pretty wild because even doing it now, you think of all the barriers you had. Well, think about what it was like in 1840 trying to map something out and you're going across swamps and woods that haven't seen anybody go through it, trying to survey pretty rough areas, trying to, draw straight lines across the state. But anyway, way it works for Wisconsin is that there's imaginary parallel east-west lines and imaginary parallel north-south lines form 6 mile square townships. So not the town that you think of, like here outside of Wausau, we have the town of Weston, town of Stettin. Those are governmental towns, but for the land description, there are townships. And east-west lines townships begin at the state's southern boundary, which is the baseline. Wisconsin only has one baseline and one principal meridian. It's called the fourth principal meridian. So everything in Wisconsin is based off of those two intersecting lines, where other states may have multiple ones, where then it gets confusing because you have to know what principal meridian and what baseline that you're running off of. But Wisconsin just has one of each. So townships are numbered north of the baseline, ranges are numbered east and west of the principal meridian. So this is what it looks like. So if I say township 24 north, range 16 east, I go 24 townships north, or I'm in the 24th block of six north, so 23 times six, whatever that math works out to. I did something very difficult, but 120, what is that, 132, something like that, north? No, 138 north. So 138 miles north, and then I forgot what I even said now. 20 east. So 20 east. I'll make it 20 east because it's easier. So 20 townships east. So 19 times six. You're looking at one 114, and then somewhere's between 114 and 120 is where we're at. So by having that town and range, it can map everything out in the state of Wisconsin. So once we have that and we know what 6 mile by 6 mile block we're on, so like this township, we don't have any south because everything's north of that line. But the first township north is 6 miles by 6 miles. And then we take that township and break it out. Each township is made up of 36 sections. So each section is 1 mile. So 1 mile square, 2, 3, 4, 5, 6 miles square. And for whatever reason, they start in the upper right and they do a serpentine back and forth. Why they do that, I don't know, but that's what they came up with. And so again, 6 by 6, 36 square miles makes up a town and a township range block. And then within that block, we can divide it out into a quarter section, northwest quarter, southwest, southeast. And then in that quarter section, so this is the northeast quarter, we can break it out again, the northeast quarter of the northeast quarter, or the southeast quarter of the northeast quarter. And so we can break that out. So for instance, this star here is in the southeast quarter of the northeast quarter of section 13 of township 2 south, range, here's the principal meridian, 1 2 west. So that's the legal description: southeast quarter, northeast quarter, 13 2 south, 2 west. So quarter descriptions, they can break down. If you want to know 1 square mile here, a quarter section is 160 acres. A quarter is 40. So why in the U.S. do we have people talk about, oh, I got the 40 or the back 40? Reason we have a 40 and not a 50 or 100 as our base is because 1 mile into a quarter is 160, into a quarter is a 40. And so that's our land division. And then some other odd ones here. I mean, our imperial system, we have a lot of great divisions. Instead of 1 kilometer is 1,000 meters, is how many ever centimeters or millimeters or whatever, nice divisions by 10. One section is a square mile is 50 to 80 feet, which is equal to 80 chains, those surveyor chains, which is also equal to 320 rods, which is a real nice description, because a rod is a very handy 16 and a half feet. A chain is a very handy 66 feet, which is 4 rods long. So you may have heard somebody say something like, I got a road easement, and how wide is my road easement? It's a 4 rod easement, or a 2 rod easement or something like that. 4 rod easement is a 66-foot wide easement. Also happens to be a lot of time what a lot of town roads are. Is there a 4 rod easement or a 4 rod town? A chain is 100 links, those 100 of those sections in there. So yeah, it's very interesting. Square mile, 640 acres. So 1 acre is 43,560 square feet, which is 160 square rods or 10 square chains. Well, there we go. We got a decimal. 10 square chains. Everybody measures that. 10 square chains. So anyway, just some interesting archaic surveying. But anyway, so you can sort of see how we can break stuff out to the quarter, or you could even do a half, the north half of the southwest or the west half of the southeast, things like that. A meets and bounds description is a little more difficult. A meets and bounds is basically you have a starting point and then you just measure from that. So here they would say, east, 424.26 feet, and then bearing at 45 degrees southeast, for 150 feet, and then bearing 45 degrees southwest for 200 feet, then bearing west for 141.42 feet, and then bearing north at 45 degrees for 350 feet. So a meets and bounds will define an area and bring it back to the starting point. Never the real nice 45-degree angles, but yeah, meets and bounds is a little more archaic, a little more difficult, usually in much smaller subdivisions. Subdivision plats, we can get into, subdivision name or CSM, and they'll have lots and block numbers, and they're sort of like the meets and bounds. It'll have these kind of descriptions in here for what that parcel is surveyed out to be. Be aware that on subdivisions, doing the soil test or looking at them, there may be restrictions. Outlots may have a restriction on them that no building or mound only. So be aware when you're going out there to take a look at these. If it is a subdivision, get that CSM, find out what that restriction is, or if there is any restriction, what the property lines are, stuff like that. Some of them have pre-planned systems out there. Other things like driveways, I just ran into one here, shared. It was a condo project where everybody had their own. It was all owned under common ownership, and everybody had a small spot listed for their home, but the septic could go anywhere in the common ownership. It was a really weird, convoluted thing. But just be aware if you start getting into stuff like that, subdivisions or pre-planned or condo units and stuff like that, that it gets a little bit difficult. Also in the southeast, we start to run into things like stormwater retention or infiltration areas or easements, whether it's utility or a stormwater corridor or a environmental corridor or something like that, where you can't put a system because there's an easement or a restriction there. Want to mention a little bit about some of the surveying. I don't know many people out there with an optical level anymore doing it, but a laser level, works the same. And if you have the money or the wherewithal to buy, some more of like the total stations or something like that, even better yet. But we're still going to go through it just so that you understand the concepts of the surveying. So we have a point here where you have somebody, whether it's the laser level setup, and then we have a stick reading. So whether somebody's optically looking through or you got the laser, and then we have the stick. So a back site is always back to the benchmark. So think benchmark starts with B, back site is to the benchmark. You match those up. So what we're doing is we're reading here wherever our instrument is set at, whether, typically a laser level. If we know that whatever that nail in the maple tree is at 100 foot, but I'm reading 3 foot on the stick, what does that really mean? My line of sight from this instrument to that stick shows it is 3 feet. Actually, I'm reading 3 feet above that nail. And if that nail is 100, the back sights we add. So 100 plus the 3 foot reading means my instrument is actually at 103 feet because I'm reading 3 feet above the benchmark. So benchmarks, back sights we add, and then foresights are forward to a location, an unknown, and we subtract off of that. So for instance here, and we'll have a table that'll make more sense, but so if the benchmark's at 100, I'm reading 3 foot, means my instrument's at 103. If I'm reading forward here to 3.1, this site or this elevation here is 3.1 below 103, which is my height of my instrument. So it's actually 99.9. And so we'll see. I believe I got some things that, yeah, we'll show some of that here. So the elevation is the point, the vertical distance above a real or imaginary. Some people will tie these in, especially if you're like near a lake lot or near like if you're in that floodway or flood fringe and you're tying into an elevation that's a mean sea level elevation. Sometimes they'll see people tie that in, but most soil testers just set an arbitrary point, call it 100, and base it off of that. And you can do that. You can do it either way, a benchmark that you set, or if it's something that you're shooting off of, like you're adjacent to a bridge and the bridge is a known elevation above sea level or something, you're tying into that, you can do that also. So again, differential leveling, backsite we add. Backsite is taken to a known elevation, usually a benchmark. So like this, just as we said, if you have your height of your instrument here and you're shooting back to the benchmark and it's reading 3 feet, here is what I'm reading. This is here at 100. I'm reading at 3 feet more. This means my instrument is actually 3 feet above that point. And then we go forward here to our unknown point. If I'm reading 3.1, that means I'm at 99.9. So how to do this? This is sort of a little table for us to put out. So again, our back sight to our benchmark is 3. Height to instrument is now 103. And then each of our different sites that we look at, going forward on them to our forward sight. If we're reading 3.1, then we're at 99. So what we do is our elevation here, 103. Front sight's 301 or 3.1. We subtract that off of our height of our instrument back here, and we're at 99. So this once we've done one back sight, then everything else that we look at, we're subtracting off of that 103, our height of our instrument. So anything else that we're doing here, once we calculated that, everything else is 2.5. We subtract that off 103. We're at 100.5. We're at 3.4. Subtracted off to 103. We're at 99.6. Seeing 3.2. Subtracted off to 103. We're at 99.8. So that's how to do that. So it's important to get contours or get elevations because we need to know where the pits are at. We also need to develop contours on the site so that we know which way the land is sloping and where we can put a system. So why do we need them? Well, it says right here in 385, we have to have ground surface contours at an interval appropriate. Now, obviously, if it's a steep site, the contours can probably be farther apart. If it's a very gentle site, we probably don't need a lot of contours because there isn't much to report. And then orientation, we have to put the longest dimension of a treatment dispersal component oriented along the surface contour unless otherwise. So contour intervals, if you've seen those, a contour map, you may look something like this up at the top. You see some concentric circles or lines. So here's a top view of it. And what this looks like is we got a peak here, a peak here. That's our peak, another peak, something what it looks like. So it's a vertical distance. So everything on this contour line is the exact same elevation. You'll never have lines cross because if this is 100 foot and this is 102, I can't have 100 intersect with 102 because then what if they intersect, what is it? Is it at 100 or 102? I can't have both elevations at the same time. If they're really close together, it's very steep because if I'm 100 here and then I got bang, 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 a bunch of them here real close to each other, it's going up very fast in a short distance. It's going to be very steep. If they're far apart, it's going to be much shallower. So here's a map and shows you some contour lines on here. You can see this one's marked at 1,000. This darker line is at 1,000. This one's at 1050. So the lighter lines in here are 10. So 1050, 1060, 1070, 80, 90. Oh, sorry, that's I'm going the wrong way. 1,000, 1,010, 1,020, 30, 40, 1,050. Anytime you have a V like this, it points uphill kind of thing, something to be aware of. Real close ones like this is steeper areas. This is steeper areas. These are far apart. It's a very gentle slope, shallow slope, things like that. So just the things to be aware of when you see them. Also, you'll see them point upstream. You can see the creek here as it cuts down. This V shape here points uphill, also points upstream. So contour lines, I mean, if you don't have the total stadia where it just maps everything out for you, there's a couple different ways to do it. You can use your level, and this is where flags come in really handy. So I could go out here and just mark out every time I see 100 foot, I just start putting a flag, and then I can sort of draw it on, with my eye to say, okay, I can see these. I can see sort of the contour of 100. I got a different colored flags. And I can see where 98 is, or I can see where the line to 96 is, and I can sort of fill those in and get the idea of where those are. The other thing that you could do is you want to be more accurate. You can actually map these things out from your own benchmark. You can map these out and say, okay, I'm, whatever, I'm, 25 feet here and 25 feet here, and I have a spot that's at 100 feet, and I can map that out. To do that is going to take a lot of work. You may want to put them in straight grid lines, or off of here, just measure along and then see, okay, I've got my first one at whatever 52 feet, the next one at 60, the next one at 70 or whatever, and then you can map those out and then draw your lines in between them. That's a better way to do it. But otherwise, what you're doing is then making your contours. So these are all equal data points. All the hundreds should be connected. All the 98s, all the 96s can't again cross, and they should make sense like that. And then here you put your pits on, and then you'll be able to map those out, what your elevations are, and then have your system suitability on the site. You could also do it in a grid pattern. The other way is just doing a grid, like let's say whatever, every 10 feet or whatever, I just measure a point. What is it? 10 feet, measure a point, and I'll come up with a grid like this. And then you could extrapolate through that. Both of these were on the 100. These all happen to be on 99, so I can connect those. These are on 98.5, so the 98 contour is between 98.5 and 96. You can sort of extrapolate. 98's got to be between 99 and 96.5. I can extrapolate between those and you can draw the lines in. You can do it that way also. Different way to be more accurate. Those in red dotted lines are sort of where it would maybe continue, but we're not mapping that because we don't know. But don't guess where they are. If you didn't map it out, don't assume. So land slope, determining that, direction, the percentage of land slope. You should be able to guess on your contour lines which way the direction is, but to determine the actual percentage of land slope is just, rise over run is commonly what's said, or the change in height over the change in length, or the change in the rise over the change in the run. So the change in height or rise over change in length or run times 100 is your percent slope. So for instance, if I am here and I'm measuring back, this is an old level that you could sight through. So if you're here and you're measuring back and you know that you're meeting the ground here and you know that you're 100 feet away and you're 6 foot tall to your eye. So a change in 6 feet of height over 100 feet is 6 out of 100 is 6%. You can also calculate that. So if you have, these plot plans like this, you can measure and say, okay, I know from, here to here, I'm changing 5.5 feet, and you measure 5.5 feet over whatever this distance is, let's say 100. So you change 5.5 over 100, you have a 5.5% slope. That'd be the other way to do it. So that's how you can measure those out and determine your percent slopes. I do recommend you measure it out once in a while. We get some in, and somebody will say it's a 6% slope, but you have it mapped out. We'll measure it, and then we'll say actually it's 10 according to what you put on the plot plan. So make sure that you're mapping stuff out correctly. But land slope and position, steep slopes affect not only construction practices. It's hard to get a backhoe out there or drop a tank or do equipment on very steep slopes. Also affects our design. That anything over 25% slope, we're probably not using a component manual. We're going to have issues out there. So make sure that you understand what the slope is. And on steep slopes, probably not a place we want to be. And also just where we're at on the landscape position. For instance, if you're up on the headlands as opposed to on the bottom, like we looked at that one cornfield, if we're down on the low spot, we're collecting all the runoff instead of being a spot that we're shedding the runoff. Land slope shapes, we want to be on a convex site, either a uniform plane or a convex. If we put the system here, we have everything is converging on the system area in a concave site, as opposed to a convex. If we put the system here, stuff is flowing in directions away from it. So we don't want to put our systems in a concave site. So that's something else to be out to look for when you're out there siting stuff. We don't want to be in an area where water's collecting, surface water's collecting. So what do we install on a contour? Again, we want to dilute concentrations. We don't want to make them more concentrated. Distribution cells can remain shallow. We don't want to have significant elevation changes. If we put a system out here, again, if even if putting a conventional system in below grade, we don't want it crossing here and having part of it stick out of the ground and then enter back into the ground, things like that, or have to bring in cover. And then also linear loading rate considerations too for us. And we looked at this yesterday, but again, we're replacing a system. We want to go with the slope parallel to it, not perpendicular. And we can't put systems in like this. We're going to concentrate it as opposed to spreading it out. Horizontal setbacks, want to mention some of those in here. Be aware that when we're testing an area, we're looking at what our horizontal setbacks are going to be. So treatment tanks and then our drain fields. So our treatment tanks have less of a setback. Drain fields are more of a setback because of the dispersal component and getting rid of that water. So make sure that we know what we're testing. Small lots are always an issue for us because with our setbacks, it's hard to get everything to fit in there. But be aware of what those setbacks are. Is that we have to maintain 50 feet from in situ component, whether it's a mound or a conventional system, 50 feet to a navigable water, 5 feet to property line, 10 feet to buildings. For tanks, we get by with less, but make sure that you're testing enough of an area. Don't have it in here, but NR 811, 812 are the well codes, mostly for wells, for public or for private wells. We're talking 50 feet for a drain field, 25 for a tank. So be aware of those when you're testing on an area. Don't test an area right next to somebody's well or within 50 feet of the navigable water, because when the designer gets there, they're not going to be able to use it. Didn't test a good enough area. So make sure that you're aware of the setbacks. We measure from them. The buildings are measured from the footing foundation, that kind of thing. We don't count roof overhangs. So here we have a post supporting a deck. That is where we measure from. We have to be 5 feet from a tank to a support post on a deck. Deck can be cantilevered over it as long as we have access to get in here to pump or service or whatever, but it's a support post. Window overhang or the roof eave, we don't measure from. We measure from the footing or foundation to like our distribution cell has to be 10 feet. So just be aware of where we measure from for building setbacks. So horizontal setbacks, things to again be aware of, you know, tanks to wells. Don't forget neighbors' wells. We've seen some of those that the well on a property line really limits what you can use. Lake shore, things like that, high water marks. So at grade and below grade setbacks, we measure from the cell, so cell to the building, 10 feet, building 10 feet, 5 feet from the cell. If you do have like an at grade and you're filling around it, the fill can't be across the property line, but we're measuring from the cell for the setback. The well is 50 feet from the cell. Mounds are a little bit different. They're somewhat similar, but we measure to the total. Be aware if it looks like you're going to be putting a mound in, make sure you test an area that's far enough away from a well so that the designer can put that in. DNR well setbacks, something else to be aware of is that NR 812 is for residential wells. NR 811 is for community or public wells. So if you have something like a city water supply or something like a trailer park or something like that that serves multiple residents or multiple homes, there's going to be a large separation distance for that. So you may have to be much farther away, um, for 200 feet to a holding component, to a dispersal area for that community water system. If you're less than 12,000 gallons per day, at 400 feet, greater than 12,000 gallons per day, you're going to need to be 1,000 feet away. Huge distances. So just be well. Also, like things like school wells, you'd have a larger separation, 200 feet. Dispersal cells greater than 12,000 to even a private well for residents is 250 feet. So just be aware that if you're dealing with something like a school or a large system greater than 12,000 square feet or start greater than 12,000 gallons per day, you're going to need a much larger setback for them. But even with proper setbacks, things can occur. The tank was 5 feet away, but because of the steep slope here, by the time they dug this big hole in, even though it's 5 feet from the tank to the footing and foundation, time they dug this in, look what happened. They collapsed the basement wall, the foundation wall, by digging that. So other things to take into consideration, even if you're meeting the setbacks, just be aware of things like steep slopes. Even if you met the setback, still may not be enough or may not work. Verifications. Counties do on sites for all soil tests, or some counties do, but the counties can do a verification. We can do a verification at the state. Get conflicting reports. I just had a county reported to me that they had, one called it a conventional, the other called it a mound, and even though one was done several years ago, they're conflicting reports in essentially the same area. They're going to go out there and see what's going on. Sloppy reporting or inaccurate. I can't read, can't understand what you're trying to do. We're going to be out there looking at it. Poor contour lines or poor plot plans, or even things such as marginal sites or personal knowledge of the site. You're reporting a conventional system where everybody in the neighborhood has a mound or a holding tank, probably going to be going out there taking a look at that. But anyway, just have our district map up here again. If you're running any questions, you can find us on the website or otherwise ask us. We have no problem going out there and helping you understand soils, or if you're at the county, helping you enforce the soils or helping you understand them too. We're glad to train. That's part of our job. We can't be on every site with you or hold your hand for every site, but we're willing to put in the effort and time to train to get you up to speed, to get you to understand so you can do it on your own. And we don't mind. We don't mind the questions. We don't mind the calls. Frankly, that's what we're here for. So we're a resource and use us as you see fit.